Our next topic is recursion. This is very important topic because a lot of functions or the procedures can be written using recursion. That is, they can be written as recursive functions. So let us learn about them. So what are the topics that I am going to cover in this video? What is recursion? Example I will take and explain by tracing of that recursion, how to trace it, how to know the output of a recursion. Then a recursion uses stack. So what does it mean? How it uses a stack? That I am going to explain you. Then also I'll show you how to find the time complexity of any recursive function. So let us start with what is recursion. Now before showing you recursion, first of all let me remind you one thing. Here I have one example program, that is main function, and one more function called function fun. And this main function is calling this function. So how this function call is made, how it works, let me remind you this. Already I have explained you in my previous video. Let us look at it again. See, once I start executing my program, it will start executing from main function. First it will execute the first statement, then second statement, then the third statement is function call. It goes to this function, enters inside, execute first statement, second and third statement. Once it has finished, the function ends and the control come back to the same line, that is third line. If any more operations present in this line, they will execute. Otherwise, it will execute fourth line and fifth line. What does it mean by any other operations? For example, this function is returning something, and here I have written multiplied by 2 something. So the value of that function has to be multiplied by 2. So this multiplication will be done once the function has returned here with some value. Assume that that function has returned 10. So 10 into 2 can be done only if this function has returned the result. So once again quickly, program starts, first line, second line, third line, control goes here, first, second, third, function ends, control returns, anything pending that will be done, and then remaining statements. This is the important point that you should remember for understanding recursions. So let me explain you next about recursion. Let us look at a general form of recursion. So here I have an example. This is a recursive function. So what does it mean by recursive function? A function is calling itself. So if a function is calling itself, then it is called as a recursive function. So a function, inside that if you see, it is calling itself again. So this is a recursive function. Then one important thing inside recursion is, here you can see that this is a base condition. Condition is there. So there must be some base condition that will terminate recursion. There must be some method to terminate this one. Otherwise it will go into infinite calling. It is just like this. First we call the function first time, then it will call itself, again call itself, again it call itself. So repeatedly it will be calling again and again. So there must be some condition at which it must stop. So in this example, this will call itself if the condition is true, or it can stop if the condition is true. Whatever it is, at some point it must stop. So here if the condition becomes false, it will not call further and it stops. So finally, let us look at it again. A function calling itself is called as recursion, and inside recursive function there must be some condition which will make the recursion stop, terminate. So in my example, if the condition becomes false, it will stop. That's it. So let us take some example of recursive function and study how it works. Let us look at an example. Let me explain you the example. I have a main function which is having some value and calling function fun1 by passing that x, and function fun1 taking parameter n, and if the condition is true, it is printing and then calling itself. I have used a C language code here. So it's printing and again calling itself for a reduced value of n. If whatever n is, suppose n is a 5, then it will call itself for 4. So if I am passing 3 from here, what will be the result? How it works? Let us trace this recursive function and check. Now tracing. How to trace a recursive function? Recursive functions are traced in the form of a tree. So let me start tracing this one. See, inside the function there are two steps that it has to perform if this condition is true. First step it has to print, second step it has to call itself by passing n minus 1, and this it has to do only if n is greater than 0. Let us start. From here I am calling function fun1 by passing x, that is value 3. So here fun1 by passing 3. So first time it has got 3. 3 is greater than 0. Yes. First step, print n. So first step is print 3. Then what is the second step? Call itself again fun1 for 3 minus 1, that is 2. So it will call itself again by passing fun of 2. See, inside the function there were two steps. Both the steps I have completed. First step was printing and the second step is call. So printing is nothing but the output. So what is the output I got so far? Output is 3. Then what about this? It's a call again. Whether this call has finished? No, it has completed first line, second line. It has not yet came out of the function. It has not yet came out of the function. It has to come out. But it is calling this one. So let us execute this. Fun of 2. Again start. 2. 2 is greater than 0. Yes, 2 steps. So the first step is print 2. So the output 2. Then call itself for n minus 1. So fun of 1. Now still this call has not finished. It has printed and it has to call this one. So again a new call, fresh call. Again a fresh call. So that fresh call is fun1 with 1. So fun1 with 1. 1 is greater than 0. Yes. So perform two things. First step, print 1. So in output we get 1. Then the second thing is call for 1 minus 1. So fun1 of 1 minus 1 is 0. Now fun0. Fun1 of 0, n, that is 0. Greater than 0? No, it is not greater than 0. It will not enter inside, so it will not perform these two steps. And it does nothing. So no printing and no calling, and it will not enter inside, and it will come out of the function. So this call doesn't do anything. So there is no further calling. Then what it has to do? It will go back to the previous function and come out of the function. So this function finishes. It go back to the previous function that is in this line and come out. Afterwards there is nothing remaining, so it will simply come out and go back to this function and comes out of this one. Then it will come back to main and terminates. So from this call it goes back to the previous call and then previous call, just like the way just now I have shown you how a function terminates and it goes back to the place from where it was called. So this is a tree, and this is called as tracing tree of recursive function, and this is the output. Now I will take one more example and show you. So this example I'll just move it aside, then I'll use this portion for showing you next example. Now I have one more example of a recursive function. This is more similar to the first one. Let me compare them and show you. If you check the main function having variable x and calling function fun1, here also main having variable x and calling function fun2. Inside fun1, it is taking parameter n and n greater than 0, two things are done. Here also taking parameter n greater than 0, two things are done. But the difference is, here it is printing and then calling itself. But here, first it is calling itself, then printing. Then what will be the output? So let us trace this one. So this is a minor difference between these two functions. Let us trace. So from here I start. First main function is calling this function fun2. So by passing value 3. So first time function fun2 will be, this is 3. 3, n is 3, so 3 is greater than 0. Yes. So first statement is what? Call itself for n minus 1. Second statement is print. So first statement, it will call itself for fun2 of 2. N is 3, so 3 minus 1, 2. Then what about the next statement, printing? It will not be done. First, this call has to finish, then only it will print. So let us take this call. Let us finish this one. So it will call itself again with n equal to 2. 2 is greater than 0. Again, 2 steps. So first step is call with n minus 1. So n is 2. So it will call itself for fun2 of 1. And second statement, it will be done after this first statement has finished. So what is the first statement? Fun2 1. 1 is greater than 0. So call itself for n minus 1. So again next call, fun2 of 1 minus 1 is 0. And printing, that will be done afterwards. First this has to finish. Now fun of 0, that is fun2 of 0. 0. 0 is greater than 0. No. So it will not enter inside this if block. And it will come out. So it does nothing. So this call with parameter 0 has terminated. Now once this call has terminated, the control should go back to the previous call. So previous call was this one. It was called from here. So it will go back to this function call in this line. This line was this one. So this has finished. Now the next line is print n. So what is n value? 1. So it will print 1. So the output is, first output is 1. Then it will go back to this previous call. And second thing that is remaining here, that is printing. Printing it has to do. So the value 2 is printed. Then this will come out of this and finish. So this call finishes. It goes back to the previous call. In that call, it has completed this fun of 2. You can see that this complete fun of 2 is in deep. It is completed. Then the second statement, print n. So the value of n is 3. So this is 3. So this is the output of this function. So you can see that the function values are 1, 2, 3. And here the output was 3, 2, 1. Now let us compare them. In this function, first the printing was done and the recursive call was made. Print and then call. Print and then call. Print and then call. But here, first call is made, then printing is done. So first call, then call, then call, then call. So again now return back. Print, return, print, return, print. So here printing was done at calling time. Before the function is called, printing was done. But here printing is done at returning time, when the function is returning to the previous call. So at the returning time, printing is done. And the difference here is printing is done after the function call. So that portion will be done at returning time. So I have shown you the differences between them. Now let me take one example and show you the differences among them. See, suppose there is a room and there is a bulb in a room and there is a door. And from that room, you can enter into one more room. This is the door for it. And there is a bulb fixed in this one. And one more door. There is a bulb fixed in this one. This is room 1 and room 2 and room 3. 3 rooms and each room is having a bulb. Now, if I give you the instruction saying that switch on bulb, second step is go to next room. So these are the 2 steps if I ask you to perform recursively. So there are rooms like this, right? So nested room, room inside room. Now, if I make you stand here and ask you to perform this recursively, then what you will do? Let us check. You will switch on bulb, first step. Second step, you will go to next room. So the first bulb that you have switched on is 1. Let us call it as output. Then you will enter into next room. Then here what you will do? Again recursively. So switch on bulb. So you will switch on second bulb. And then go to next room. You will enter this next room. Then in this room again first step is switch on bulb. So you will switch on third bulb and go to next room. There is no next room further. So it was more like a recursive call, a function calling itself again and function calling itself again. Now this is termination. There is no next room. What you will do now? you will definitely come out of those rooms. Your work has finished. So from third room, you will come back to second room. Now, will you do anything now? No, you will simply come out. You will come out in the first room, then you will come out of the first room also. So third to second, second to first, then you will come out. And you simply come out. Nothing you will do. So it means first stage was you were entering in. So it was just like a calling. And after you have finished this one, you cannot go further. So you will return back. So this is returning. So you have gone through two phases. One is a calling phase, other one is returning phase. Or I can say that this was ascending and then descending. So you were going to next, ascending. Then you came back and back. So descending. So you have done ascending and descending. And at descending time, you have not done anything. Now, I'll give you one more example. First step is go to next room. And second step is switch on bulb. These are the two steps. I have changed the order, you can see. Go to next room, then switch on bulb. Now let us see if these are performed, then what will be the result. If you are here, then I have given you two instructions. Go to next room. Then second step is switch on bulb. So first what you will do, you will not switch on bulb. You will go to next room. Then there, again the first step is go to next room. So you will go to next room. There, again the first step is go to next room. So there is no next room. There are no rooms further. Then you will perform second step. Switch on bulb. So the first bulb to be switched on is third bulb. Then definitely you will come back to the previous room. And in this room you will switch on second bulb. And you will come back to the first room, switch on first bulb. That's it. So I have two different versions of steps here. In first set of steps, switch on bulb, go to next room. So the bulbs were switched on in this order, 1, 2, 3. So where is the recursive call? This is the recursive call. First perform the operation, then the recursive call. Here, first the recursive call, then perform the operation. So the main important thing that I have to show you here in recursion is that recursion has two phases. One is calling phase and the other one is returning phase. So bulbs were switched on while going, bulbs were switched on while returning. So if you see this recursion, print and then call, switch on then go to next room. So this is same as that one. And if you see this one, go to next room then switch on. So here in this example, first go to next room, that is make a call and then print. So this is similar to this one. So finally I can say that recursive functions are just like a rubber band. If you stretch a rubber band, pull it, so next. If you release, it will come back. So same way, recursive function call and then return. So there are two phases. So that's how these are compared. But one thing that may confuse you, just let us look at this one. See, the first value was 3 to 1. So the printing was 3 to 1. But here the room numbers are 1, 2, 3. Don't compare this with that one. Just understand the procedure, how it is working. Otherwise, I can change the room numbers 3 to 1 also. So the output will be similar to them. So the important thing that we have learned here is that recursion will have two phases. One is calling phase and one is returning phase. Now I'll write a general form of recursive function once again and show you. Yeah. Here I have a function, a recursive function. It is calling itself. There are three statements. First statement, there is something, and then it is calling itself, and there is one more statement. So the question is, when this statement will execute? This will execute at calling time. And when this statement will execute, it will execute at returning time. And if anything is there followed by this function, then that will also execute at returning time only. If any computations are there, any more things are there. So that's it. So from this, like you can take it as a formula. In a recursive function call, before the function call, if anything is there, then that will be executed at calling time. After the function call, it is executed at returning time. So we can call this portion as ascending and this we can call it as descending. So recursive functions have two phases, that are ascending and descending. So the main important thing that we have learned now is that a recursion will have two phases. Let us compare recursion with loop. Loops are repeating statement. Then what is recursion? Recursion is also repeating. See a function call, then again it is calling, again it is calling. So is it not repeating? Yes, a recursion is also just like repeating. But the difference is a loop will have only ascending phase, but a recursion will have ascending as well as descending phase. So that is the strength or power of recursion, that you can utilize or exploit it for writing code easier. So these two phases are there. So the descending is there only in recursion. So that's all. I end here in this video. Then in next video, I'll show you how stack is used in these two recursive functions, and also I'll show you the time complexity. So we'll continue with the same functions in the next video. Now let us look at how recursion uses stack. So I'll take this first example and show you how the stack is utilized. Now already we have seen this model of memory, that the memory is used by dividing into three sections. One is code section, and here I show stack, and this is heap. Now in my program I have two functions, that is fun1 and main. So the machine code of those two functions is already there in code section. Now let us run the program and see how the stack is created. See, the program starts executing from main function. So the first function is main function. In that main function, this is the first statement, that is X is created. So an activation record for main function is created, and it will have its own variable, that is X, having value 3. Then the very next statement is fun1, a call to function 1. So once the function 1 is called, it is having just one variable, that is n. This is the only variable. So activation record for that fun1 is created, and it will have that variable n, and this value X is passed to that one. So it will be 3. So this is for main, and this is for fun1. I'm showing you line by line how it is working. Just let us look at it once more. See, the program start executing from main function. The very first thing is X. So activation record for main, and X is created. The value is 3 and the function is called. And that function is having just one variable, that is n. So activation record is created for fun1 with variable n and having value 3. Let us continue. If n is greater than 0, yes, this 3 is greater than 0. Then printf. So as per the tree already we have seen that a 3 is printed. Then the next call, function fun1 is called once again with a reduced value of n, that is decremented value n minus 1. So that function is called again. So once the function is called, we know that activation record will be created, and in that again variable n, and that will have the value 2 this time. This is also activation record for fun1, and this is the second call. Now in that second call, again it checks if n is greater than 0. Yes, 2 is greater than 0. So printf, so 2 is printed. The next line, call again with n minus 1. So right now n is 2. So again a new call, again an activation record is created, and variable n is created with value 1. And this is again a call for fun1. Now again, if n is greater than 0, yes, 1 is greater than 0, print 1, 1 is printed. Then again call fun1, with reduced value, decremented value, n minus 1. So again an activation record for fun1 is created, and it will have the variable n, and that value is 0. This is a call again for fun1. This time, as n is 0, when it calls again, n is greater than 0. So no, n is not greater than 0. It will not enter inside. It will not print anything. Here it doesn't print anything, and it will come out of this conditional statement. So it doesn't enter into conditional statement. So it will come out of the function. And once that call ends, this activation record is deleted. And the control goes back to the previous call. And in that previous call, what it has done, it has called this one. So the next is nothing. So that call will be using this activation record. And that also ends. So again, this is also deleted. It goes back to the previous call. In the previous call, this line is over. So there is nothing remaining. And that call uses this activation record, but there is nothing to do. So this is also deleted and this is also deleted. Then it come back to main. Inside main, after fun1, there is nothing remaining. So this also ends. So all these activation records ends one by one. So this is how stack is created and utilized in recursion. Now, one more thing. What is the size of the stack? Leaving main function, if you count the activation records 1, 2, 3, 4. So only for that function, 4 activation records are created. So size of the stack is 4. And how much memory it's consuming? Each activation record is having just one variable, n. So n how many times? 4 times. So you can see the calls here, 1, 2, 3, 4. Already we have done 1, 2, 3, 4. So already we have done tracing. We have generated a tracing tree or recursion tree. So there are 4 calls. So 4 activation records are created. And at the end of this, it will go back and go back. So activation records are deleted again. So size of the memory consumed by this function is 4 into whatever the size of variable integer is. For value of x, that is n, is 3. For value of n is 3, there are 4 calls. So for value of n equal to 5, there will be 6 calls. So for n, there will be n plus 1 calls. So total n plus 1 calls. So how many activation records? N plus 1 activation records. So we can see that the activation records, number of activation records, it depends on the number of calls. So total calls are n plus 1. And what is n? It's a variable. How much memory it's consuming? Now it is integer type. It may be taking 2 bytes or 4 bytes depending on the compiler. So we can say just n plus 1 call. So the total memory consumed by this is order of n. We can mention it as order of n. Why not plus 1 there? See, this is a polynomial, a formula n plus 1. In that, degree of the formula is 1. Highest term is n. So we take n. So we write degree there, order of n or degree of n. So we mention the space as order of n. But actually if you see, it is n plus 1 activation records are created. So from this discussion, we can understand that recursive functions utilizes stack. So here internally it takes some extra memory for the stack. So there are memory consuming functions. Recursive functions are memory consuming. So that's all I have explained this one. Now already I have a stack, then just I will show you how this function works. So I will use this program as well as a tree. Then also I will show inside the stack what happens. Let us look at it quickly. There are 2 functions, fun2 and main. Both these functions are there inside main memory. Now let us start executing. Program starts from the main function. So the first variable x. So activation record for main is created and having the value 3 in x. And it will call function fun2. Once the function fun2 is called, activation record for 2 is created. So it means all these are for 2 now. So I'll just change them. So the first call, n equal to 3. This is created. That is this one. This is created. Now n is greater than 0. Yes. Then call again. So again it will call with n minus 1. So a new call will create this activation record with n equal to 2. Then again it will call. Then again it will call. See, because the first statement is call. So it's calling itself every time. When n is equals to 0, 0 is not greater than 0. So it will not enter into if block and come out of the function. Once it come out of the function, this activation record is deleted because the function with value of n as 0 has terminated. It goes back to the previous call. In the same function, it will go back to the previous call where it has finished this one. Now it has to perform this. That is this line in the tracing tree. So what is the value of n it has to print? Now the current topmost activation record is this one, where the value of n is 1. So it will print 1. It will print 1 because the value of n is 1 here. And once it has finished, it will come out and this activation record is deleted. It will go back to the previous call. In the previous call, again, it has finished the first line, that is this line. Now it has to do this. So print n. So what is the value of n now? So the topmost activation record in the stack, you can see now n value is 2. So this is printed. So 2 is printed. Likewise, 3 is printed and all these activation record ends. So you can see that these activation records are created when the function was calling itself again and again. So this is more like ascending. Now once it has reached the last call, that is where n is 0, so it will start returning. So that is a descending. So while descending, it will utilize these values. So all the values of n are there in the stack in the different activation records. So these values are utilized at returning time. So that's all. This is how recursion uses stack. So both of these functions are almost same, only the difference is that this is first printing and then calling. This is first calling then printing. So the activation record created for these functions will be same only. So that's the reason I have taken two similar examples and I have shown you how the stack is utilized. It will be same in both the programs. The size of the stack and the space consumed by this function is also order of n, that is total n plus 1 activation records are created for function fun2, leaving aside main. This is how recursion uses a stack. Now next thing that we have to study is how to find the time complexity of recursive functions. So I will take just one example, this example, and show you how to find the time complexity of recursive function. So let me tell you the basic concept for finding the time complexity. We assume that every statement in a program takes 1 unit of time for execution. Let me give you the idea behind that one. See, suppose there are some books kept here and you have to move the book and keep it in a shelf or in a rack. How much time it takes? Maybe half a second, quarter of a second. Now for somebody who walks very slowly, may take 1 second for keeping one book there, one by one if you have to keep. So time varies from person to person. So we don't mention seconds or milliseconds, we say 1 unit of time. Like if you take the example of currency, $1, 1 rupee, 1 pound. So we say 1, but what is the market value? That may be different. So we say 1 buck or 1 unit of currency. So same way, we assume that every statement takes 1 unit of time. If that statement is repeated multiple times, then you count the frequency, how many times it is executed. So that is sufficient for analyzing our function now. Let us see what our function is doing. It's doing nothing, just printing. So it is printing a value of n. How much time it takes for printing? 1 unit of time. 1 unit of time. How many times printf is written here? Only 1 time. So it is just 1. But this is a recursive function. So it is calling itself again and again. So total how many times it is printing? So let us look at into the tracing tree or recursion tree. Here it is printing 1 time, 2 times, 3 times. So total how many units? 1, 1, 1. So I can say it takes 3 units of time for the value of n as 3. Value of n as 3. So the first value of n is 3. If I make it as 5, then it will take 5 units of time. Then for n, it will take n units of time. So it is just like, coming back to the example, if you have to keep 1 book in the rack, you are taking 1 unit of time. 10 books, 10 unit of time. N books, n unit of time. What is n? Whatever may be. So the time depends on the number of books. So here the time depends on the value that you're passing from here. It may be 3, it may be 5, or it can be anything. So we say the time taken is n units of time. So the time can be represented as order of n. The answer that we got is n units, so the degree of that polynomial is 1, so we write it as order of n. So the time taken is order of n. There is one more method of finding the time complexity using recurrence relation. I will show you how to write recurrence relation and how to solve it to find the time complexity of recursive functions. Now let us find out the time complexity of this recursive function using recurrence relation. We assume that the time taken by this function is t of n. T is for time. If the time taken by that function fun1 is tn, then that total time should be sum of all the times taken by the statements inside. So let us look at the statement. See, there is a statement. This is a conditional statement. How much time it takes for execution? Just 1 unit of time. 1. Then there is a printf statement. How much time it takes? This also takes 1. Then there is one more function call. How much time it takes? 1. As I said, every statement takes 1 unit of time for execution. So this also I have written 1. No, it's wrong. It's wrong. See, that is a function call. So I should know total time taken by that function call. So it is not just a normal statement. It will call again itself, so there is something more behind that one. So I need to know how much time that function call is taking. So let us see closely. When I said this function call total time tn, then this is similar to that one, and this is n minus 1. So yes, this will be taking tn minus 1 time. Yes, this is not a normal statement. There is a function call and it takes tn minus 1 time. Then what is this total tn? I said the sum of all the times taken by the statement. So let's take the sum. So that tn is equals to tn minus 1, the bigger term I am writing first, plus 2. So the total time is tn is equals to tn minus 1 plus 2. So the recurrence relation is tn is equals to tn minus 1 plus 2 when n is greater than 0. When n is greater than 0. What happens when n is equal to 0? When n is equals to 0, it will just check the condition. It will not enter inside and it will come out. So just checking the condition, 1 unit of time. So it takes 1 unit of time. So this is the recurrence relation formed from that function. So the time complexity of recursive function can be represented in the form of a recurrence relation. Now if we solve this using induction method, or also called as successive substitution method, we can get the answer. So let us solve this one. Now before solving this, I should tell you one thing. If you have any constant value here, then let us write it as 1. So that means constant. Now let us solve this. So the recurrence relation is tn is equals to tn minus 1 plus 1. This is the first equation we have. I can solve this if I can know what is the tn minus 1. See, here I write, since tn is equal to tn minus 1 plus 1, then what will be tn minus 1? So if this is n, replace with n minus 1, so this will be tn minus 2 plus 1. So I can substitute this one, tn minus 2 plus 1, in place of tn minus 1. So this I can replace here. So the next equation that I get is tn is equals to 2tn minus 1, tn minus 2 plus 1. So this is tn minus 2 plus 1, and this plus 1 as it is. So this is substituted with this one, and then this plus 1 as it is. So what is this one finally? tn is equals to tn minus 2 plus 2. So let us call this as second equation. Then let us substitute in this place. So what this will be? This will be tn minus 3 plus 1. So if I substitute that, then this will be tn is equals to tn minus 3 plus 1 n plus 2. So this can be written as Tn is equals to Tn minus 3 plus 3. This is the third equation. So I have substituted 2 times. How long I should do this? Let us continue it for k times. So k times Tn minus k plus k. Because this was 3, so this is also 3. If it is 4, then this will be 4. If this is k, then this will also be k. So the fourth equation I got. See, we have to solve this one. So substitute and then substitute, go on substituting until it reduces down to a smaller value, that is n equal to 0, where we know the answer, that is 1. See, when you don't know the answer for a bigger expression, you know the answer for a smaller expression, then break the bigger one into smaller one and solve it. So the same thing we have done. We don't know how much this is, but we know when n is equals to 0, answer is directly 1. So we know that. So we have tried to reduce this and by substituting, and we got this one. Now we say that this n minus k actually has become 0. So on that side I will write down, assume that n minus k is equals to 0. So it means we have n minus 1, that we made it as n minus 2, then n minus 3, and so on, up to what? It became 0. So we assume that this has become 0. So it means, therefore, n is equals to k. So in this equation, if I substitute, that will be Tn is equals to Tn minus n plus n. So at the place of k, I have written n. So n minus n plus n. So I got this one. So this is Tn is equals to T0 plus n. So Tn is equals to 1 plus n. So that's all. I got the answer. Tn is equals to 1 plus n. This can be written as order of n. See, earlier, directly from the tracing tree also I have shown you n plus 1 was number of calls. So yes, I got the number of calls here. And the time taken by this function depends on the number of calls. So yes, it is order of n. So it will be printing for n times, and the calls will be n plus 1. That is 1 more than the number of times of printing. Let us summarize the things that we have learned. See, I have shown you what does it mean by recursion, and I have shown you how to write a recursion. I have traced that one, and I have shown you 2 different types of recursion. Then I have shown you how a stack utilized, and then we saw how to find the time complexity. From the tree also I have shown you, and by writing a recurrence relation also I have shown you. And the time complexity is mostly written as order of or degree of, that is order of n. See, I'm not using the notations like big O, omega or theta because we have not discussed about them. So I'll give you the idea about these notations at some other time. Let us start a new project for looking at an examples for recursion. So I'll start a new Xcode project. Select command line tool. Then here mention the project. So I'll give the name as tail head. So the project name is tail and head. The language I have selected, that is C language. And create. A project is created. This is the main function. Now here I can add my code. So I will write on the functions that we have already discussed. That is fun function for just displaying numbers. Void function fun, which takes parameter n. If n is greater than 0, printf %d, I'll give some space, then n. Then function call itself for the value n minus 1. Now this function, I will call it from inside main function. I'll take a variable integer x with value 3. Then let us call the function fun for value of x. This is an example of tail function. The function is recursive. It is calling itself with the reduced value of n, and it will be calling if the value of n is greater than 0. So initially we are calling it for value of n as a 3. So x is a 3. I will run the program and show you what. Let us see what the output is. So here you can see the output is 3, 2, 1. So first it is printing 3, then and 2, then 1. As this recursion, we know well that a stack is utilized. A function will be calling itself again and again. So internally it uses a stack. Let us see how this recursive function will use a stack. For that, I will debug the code. So inside the main function, the very first line, I'll put a breakpoint by clicking here. So this is a breakpoint. So I'll debug the program and let us understand how this function recursively call itself and what is the behavior of a function. Run the program. So now it is stopping at this line here, x is 3. So now you can see that right now the value inside x is garbage because this line is not yet executed. 3 is not yet stored in x. And here inside this navigator window, you can see that the 0th function, that is main function, that is the starting point of a program. So it is numbered as 0 and it is main function is running. Now if I continue line by pressing F7 or function F7, then it moves to the next line. Now the value of x is initialized to 3. Now this line is about to execute. The line which is highlighted with green color, this line is about to execute and you can see the value of x is 3. And this function is not yet called. So if I put a cursor here, there is no value shown here. Let us continue. Now a function is called, it has entered inside the function and the value of n is compared with 0. Right now the value of n is 3. And here in the debug navigator, you can see that main has become 1 and this fun is 0. They are numbered. Like the presently executing is 0 and the previous one who has called it is 1. Now value of n is 3. I will continue execution. Now the next line is printf and printing is done. So the value 3 is printed here. Value 3 is printed. Now again the function is called. So it's about to call itself again by passing 3 minus 1. So if I continue next, again the function is called, it has directly entered inside and it is on the conditional statement right now where the value of n is 2. Yes. And here you can see in the debug navigator, the function on the top is 0 and the next is fun again. So function is called 2 times. And then below that is main function. Main has called this fun, then fun has called again itself. So 2 times, this is the second call. Now let us continue further. Printing is done. So value 2 is printed. Again it has called itself. This time the value of n is 1. And you can see that these are 3 calls here inside the debug window. Our main 3 function calls for fun are there. Now 1 is greater than 0, so it will enter inside and it will print this one. Let us proceed. So printing of 1 is done. Then again it will call itself with the value of fun, with the value of n as 0. So this is 0. So these are total 4 calls. So you can count here above main there are 4 function call. The topmost one is numbered as 0 and so on. Now for this, if I continue, n is not greater than 0, so it will not enter inside this if block and it will come out of the if block. It will not enter inside this if block and also it will come out of this function. So the value when n is 0, nothing happens. Printing is not done and it will not call itself. These 2 lines will not be executed. Let us continue further. So you can see that it has reached the end of the function call and right now the value of n is 0 only. So if I press next step again, then see what happens. It is still there only, but this is for the previous call and you can see that in the navigator the functions are reduced by 1. So the function with value 0 has finished. Then what is the topmost function now with the value of n as 1? Yes, it has gone back to the previous call. Now this is having value 1. Then when it goes back, this will have value 2 and this will have value 3 and so on. And at last it will reach main. So right now it is inside that function call where the value of n was 1. If I proceed further, again you can see that it is standing there. Just there was a blink that has gone to the next statement. So it is back on the same statement because outside if this is the After if it has reached here, so the value of n is 2, and you can see that the number of calls are reduced. Right now it is with value 2. Then below this one, there is one more function call with value 3. So if I continue further, it will go back to this function and this function call will terminate. Let me go to next. Now I'll go to the next step. Again, it is standing there only. Just it has blinked and came back to this function call at the end of the function call. And the value of n is 3 here right now. So you can see here in the debugger navigation that above main there is only one function call. Currently we are in that function call with a value of n is 3. Actually this was the first call. So this is how the function is returning one by one. It has called itself again and again. Now it is returning one by one. Now if I continue further, it will go back to the main function call and the program ends. See, it's back to this line from where the function was called. Here it has started, so it is back to this function call. So I'll simply finish the program now. So this was the example of tail recursion which we have already discussed on board. So I have shown you how the function calls are piling up on a stack. I will modify the same function into a head recursion by just copying this line. I'll cut it from here and paste it just before printf function. So you can see that first the function will be called, it will be calling it recursively, then it will print the value. So again I will put a breakpoint here upon this line, the first line inside the main function. Now let us run the program and see what the output is. We know the output already, that the output is going to be 1, 2, 3, but let us learn how it is generated. Running the program. Now in the debug navigator, you can see that the starting point is main function, and the main function, it has stopped in that line where we have given breakpoint. And the value of x is not yet initialized, it is garbage. If we continue further, the first line is executed and the value of x has become 3. Now it is about to call a function. And in the navigation, you can check that there is only just one main function, that's all. If we continue further, then this is the first function call. This is the first function call, you can see, and the value of n is 3. Then 3 is greater than 0, it will enter inside and it will make a call again without printing. Yeah, it has came to the line where there is a function call. Now back. Now again a function call. This time there are two function calls and right now the value of n is 2. I'll continue. Again on the function call, recursive call. So it has called again itself with the new value, that is 1. Then 1 is greater than 0, it will enter inside and again it will call itself for 0. Yes, again a new call. So value is 0. You can see that this printf is never executed. So total how many calls? We have passed 3. So for calls are for 3, 2, 1 and 0. 4 calls are there. So inside the debug navigator, you can check that above main function, there are 4 function calls. Right now it is in this function call. And right now the value of n is 0. So it will not enter inside if block and it will terminate. So this function will terminate and it will go back to the previous call. See, this is the last line. Now if I press again, now if I press F7 again, it will go back to the previous call. Yeah, it is back on the previous call. It is on the same line from where it has called itself and the value of n was 1. Yes, previous to 0, the function call was 1. Now next line it will be printing 1. Printf execute. Yes, it has printed 1 and it came out of if block. Now it's about to terminate. Function call with value n equal to 1 is about to terminate. If I continue, then it is back on the previous call. You can see that the call has reduced here. It is back on the call where it was n value was 2. So yes, here it is, n is 2. So then it will print this 2 and go back. So you can see that printf is being executed at returning time. Calling time, there was nothing in this function. So I'll continue execution. Printf 2, then go back to previous call where the value of n was 3, then printf 3, go back to the previous call, and it has gone back to the main function, and that's all. Function ends. So that's all. We have seen how a recursive function works. We have seen the calling phase as well as returning phase. Let us look at static variables in recursion. We have seen how to trace recursion. We have also seen how a recursive function utilizes a stack. Then, what if there are any static variables? How to treat them inside recursive function? So here I have an example function, recursive function. Though there are no static variables right now, without static, this function, I will trace it and show you. Then if static is introduced, then I'll show you what should be the difference. First, let us see what the function is doing. I will read it out. I'll explain what these things are. See, there is a function fun which takes parameter n. If n value is greater than 0, then it will call itself with the degrees value of n and also add n. So when this plus n will be done, calling time or returning time? It is done at returning time. Then if the value of n is 0, then it returns 0. And from main function, this function is called by passing a, that is 5. Now to show how they will work inside the memory, I have already taken a diagram for the memory where I am showing code section, both the functions are there. Then how the stack is used, I'll explain you. First of all, I will trace this function for value 5 and show you the tracing tree. First, the function is called for the value 5. So this is fun of 5. And 5 is greater than 0, yes, so it will call this one. So it will call itself for fun of 4 plus this n. So let it be blank here. That will be filled with the value of n. And what is the value of n here? 5. I'll use it afterwards. Then it will call itself for 3 plus 4 should be added. I'll leave it as a blank. Then fun of 2. 3 should be added. I will leave it as a blank. Then fun of 1. 2 should be added. Then fun of 0. 1 should be added. And fun of 0 is 0. This is 0. Now when it goes back, this is 0 plus 1. This is 1. So this will be 1. And the result of this one is 1. Plus this is 2. So this will be 3. Then the result of this is 3. And this is 3. So this will be 6. So the result of this one is 6 plus 4. This will be 10. The result of this one is 10 and 5. So this will be 15. So the result of this is 15. So this is the tracing of a function when it is called upon value 5. Now let us see how the activation records are created. Then the activation records for fun will be created. Value of n will be 5. Then value of n will be 4. Value of n will be 3. So this is how stack is created. Every time for each call, a new variable will be created inside the memory and it will have its value. That is 5, then 4, then 3, then 2, then 1 and 0. So all these values are newly created every time whenever the function is called. This we are aware of local variables of a function. Now I am going to make changes in this function, then we will see how to handle static variables. So I am making modification. Static variable. Integer x whose value is 0 initially. And before calling, I'll be incrementing it. And while returning, I'll be adding x. So this is not adding n, adding x, and x is incremented and it is static. So first of all, where these static variables are created, they are created inside code section. Or there is a subsection of code section called as a section for global variables and static variables. But I'm showing directly inside code section. And the value of that one is 0. Will this static variable be created every time whenever the function is called? No, it will not be created every time when the function is called. It is created only one time, that is at the loading time of a program. So this x will not have multiple copies just like n. It will have a single copy. So all these calls of this function, they will use the same copy of x. So I cannot have a separate copy each time like n. For n, every time a new copy is created, but for x, there is a single copy. Now, what will be the result of this function? For that, I will trace it again. So for that, I will remove these things and I will trace it again. Let us look at the tracing and see how static variable should be handled. For a static variable, it is x. So I should have a single copy of static variable separately. Don't show it in the tracing tree. Now let us start. First time the function is called by passing value 5. So n value is 5. First time fun of 5. Then if n is greater than 0, yes, it is greater than 0, x plus plus, this x becomes 1. Then call itself fun of 4 plus this x will be added at returning time, so use it at returning time, don't use it now. Continue for this call. Again 4 is greater than 0, x plus plus, so this x becomes 2. Call function of 3 plus x should be added at returning time. Then call greater than 0, x plus plus, call itself. So 3 call for 2, x plus plus, then plus this x should be added. Then for this call, again this is 4 and call for 1 plus x should be added. Now for this call, this becomes 5 and call for 0 plus x should be added. Call for 0 returns 0, so the result of this function is 0. Now it will start returning back from here. So this is 0 plus x has to be added. So what is x now? 5. So this is 5. Result of this is 5. Then x should be added. What is x now? 5. So this is 10. So the result of this function is 10. Then plus x should be added here. So what is x now? 5. So this is 15. See, in the previous example, we were adding n. So n was having its own value in each call. So those values were used. But now there is only one single copy of x. So each call will use that same copy, and right now it is having value 5. So that same 5 is utilized by all. So this result is 15 plus 5. So this is 20. Then 20 plus 5 is 25. So the result of this function is 25. So that's it. This is how you should handle static variables. If there are any static variables inside recursive function, don't show them in each step of tracing tree. Write them just like a global or outside variable and maintain a single copy of it. So sometime we need to use static variables also in recursion. So I have shown you how they work. Now if it is not static, if I take out this variable and if I declare it outside like a global variable, then also the result will be same. So static variable will have a single copy, and even global variable, it will have a single copy used by all the function calls. And those global variables are also created inside code section. And every call will use the same copy, and the result of the program or the function will be same. So in the previous example, the result was 15, but now for 5, the result is 25. So here in printf, result will be 25. So in the coming examples, we will use this recursive function with static variables. In this demo, we'll look at static and global variables in recursion. I'll start a new project, command line tool. I'll give the project name as static global. Create a project. Project is ready, and here is the main function. I will write down the function that I have shown you. Integer is the return type of a function, and the parameter it takes n. Now inside this, if n is greater than 0, return fun of n minus 1 plus n. Otherwise, return 0. This is the function we have seen, which gives the sum of first and natural numbers. Let us take a variable r, and inside this r, let us get the result of a function by passing parameter 5. and I will print the result obtained by that function. Percentile D, only one value, that is R, I have to print. Yeah, this is the function already we have seen. The value, if we pass the value as a 5, it returns 15. I will directly run the program and let us see what is the output given by this program. Here the output is 15. Yes. Now I will modify the function. I will introduce a static variable inside this function, static integer x, initially 0. And before calling itself, let us do x plus plus and return plus x. This is what I have explained you on the board. So the same thing I have written here. And when we have traced that function, the result was 25. Let us run and check what the result will be. Here after percentile D, here inside printf after percentile D, I will give /n, so it gives a new line after printing the result. Let us run the program. See, the result is 25. Let us debug this program and see. So for debugging, I will take a breakpoint. Then I run the program. It will stop here at the breakpoint. Inside debugger window, you can see that just it's in the main function and it has stopped at this function call. I will continue running. Next line. Now the function is called. You can check the value of n is 5 and x is right now 0. The next statement, it will do x plus plus, then it will call itself. So now you can see that the value of x has become 1 and this is the second call. Here in the debugging window also you can see that there are two functions calls, but the value of x is 1. Let us continue. Now x plus plus, value of x becomes 2. You can check it here. See, x value is 2. Then again it will call itself. Again it will call itself. Again it will call itself. So right now n value is 1 and x became 4. And then next statement, x becomes 5. Now n value is 0 and x is 5. Now for 0 it will not execute, it will not enter inside if block and it will return 0. Yeah, return 0. So it goes back to the previous call. Now in the previous call the value of n was 1. Now it's about to add this value. See, the value of x is 5. 5 is added with this one. Because x is static, there is only one copy of variable x. And here inside this wash you can see that x is 5 and n is 1 at the bottom. If I continue, it will go back to the previous call where the value of n was 2 and x is still 5. Then continue, it will go back to the previous call where the n value is 3 and x is 5. Because when it has reached till n equal to 0, by that time x became 5 and x remained 5 while returning time also, because there is only one copy of variable x. If I finish this, then here in the next line the value is 25. Yes, we got the same result. So we have seen how the function is working. Now I will modify this function. I will remove the breakpoint. Let us modify this, and instead of static variable I will remove this and I will make it as a global variable. Out x assign 0. So this is a global variable outside all the functions, so it's accessible to all the functions. Now I will run this. Answer is 25. So it's working same. Now I'll show you one thing. See, here I have called the function for 5 one time and I have displayed its result. I will do it again. So again I will call the function for value 5 and again print the result. So if you check this variable x, that will become 5 in the first call. Then the second call it will become 10. Then the second call it will start from the same value 5. So let us see, when I call the same function for 2 times, then what will be the result at 2 times? It will not be 25 at both the times. See, first time it is 25 and the second time it is 50. The reason is when the first call is made, it has made the value x as 5. Then the second call is again trying to increment x for 5 times, here x plus plus, then x will become 10, and 5 times 10 is added, so it is 50. So that's all. We have seen the effect of static variables and global variables. Sometimes they are very useful. Some type of problems we cannot write them in the form of some functions, we cannot write them recursive. We may have to use static variables, so we will see them when we come across such topics. Now we'll start the next topic, that is types of recursions. So here are the list of types of recursions. I'll be discussing each of them one by one by taking some examples. See, the tail recursion is the first one, then head recursion, tree recursion, indirect recursion, and nested recursion. So we'll look at them one by one. Let us start with tail recursion. Yeah, here is the first recursion, that is tail recursion. We have already seen this type of recursion. This function already I have explained in the previous video. Now it is a tail recursion. So what does it mean by tail recursion? If a recursive function is calling itself, and that recursive call, this is called as recursive call, and that call is the last statement in a function, then it is called as tail recursion. After that call, there is nothing. It is not performing anything. So it is called as tail recursion. For example, this is fun and taking some parameter n, and if n is greater than 0, the similar one I am writing, and there are some statements inside, then the last thing is it is calling itself by a reduced value of n. See, what all it has to do, it is performing first, then it is calling itself. So in this example, I have just written printf, but there may be a lot of things a function may be doing. All those things it has finished, then it is making a call to itself. So if it is a last statement, then it is called as tail recursion. So this means that all these operations will be performed at calling time only, and the function will not be performing any operation at returning time. Everything is performed at calling time only. So that's why it is tail recursion. Now suppose there is something written here, plus n, means along with the function call some operation is done. Then if this is the case, then when this operation will be performed, this will be performed at return time, because unless the result of this function is known, addition cannot be done. The value of the function is added with n, so this addition can be performed only at returning time. So in this function there is something remaining that has to be performed at returning time, so it cannot be a tail recursion. Tail recursion means at returning time it doesn't have to perform anything at all. So this is a perfect example of tail recursion, or else if I remove any processing here, then it is a tail recursion. Now next I will compare tail recursion with loops. Now comparison of tail recursion with a loop. So first and the foremost thing I have to tell you is that every recursive function can be written as a loop, or vice versa. Every loop can also be converted in the form of a recursion. But now let us compare tail recursion with loop. See, this is a tail recursion. Already you know the answer in the previous video. Already I have traced this one and shown the output. If we call this function by passing 3, so it will print 3, 2, 1. And it will stop when the value of n becomes 0. So it will print the values 3, 2, 1, and it will print in calling phase. Now same function, I want to write it using loop instead of recursion. So I will write on the function here void fun, which it takes parameter n, and the first thing is n greater than 0. I will write n greater than 0. But instead of if, I will write it as while. Then inside this printf statement, this is printf percentile d and some space n. Then calling function again itself by reduced value of n. So let us do n minus minus. That's it. So if I call this function by passing value 3, then 3 will be passed here, then it will first print 3, then it will make 2, and again repeat. So print 2, then repeat, print 1, then repeat, it is 0, so it will stop. So this will work same as that recursion. As it is, I have converted, just instead of conditional statement, I made it as a loop. Instead of conditional statement, I made it as a loop, and instead of function call with reduced value of n, decreased value of n, I have just written n minus minus. So the function is same as that one. Output is same, and the structure also, if you see, it looks more similar. That's what. So the point that I have to tell here is that tail recursions can be easily converted in the form of a loop. Now let us decide who is efficient. In terms of time, if you analyze, this is printing 3 values and this will also print 3 values. So the amount of time spent is same. Whatever the value of n is given, if it is 3, then it is 3. If it is 5, then it is 5. So it means the time taken by both of them is order of n. So time is same. So the time taken by both of them is same. So the time is order of n. But let us analyze the space. This is a recursive function. It internally utilizes stack. So for the value of 3, it will create a total 4 activation records in a stack. This already we have done the analysis. So for n, the space taken by this one is order of n. But what about this one? This is a loop function. So how many activation records will be created? Only one. It is not calling itself again. So the space complexity for this one is order of 1. So it will just create only one activation record. So that is constant. So we say it is 1, order of 1. That is constant. So there it is order of n, and here it is order of 1. So the conclusion is, if you have to write a tail recursion, then better you convert it into a loop that is more efficient in terms of space. But this will not be true for every type of recursion or loop. In case of tail recursion, loop is efficient. And even I have to tell one more point, that some compilers under code optimization inside compiler, they will check if you have written any function which is a tail recursion, then they will try to convert it in the form of a loop. It means they will try to reduce the space consumption and they will utilize only order of 1 space. So your function will be converted into object code just like a loop where the space is reduced. So that's all about tail recursion. Now next we will see head recursion. Now let us see head recursion. See, this is a structure for head recursion. If there is a function that is calling itself, so it's a recursive function, then the first statement inside the function is recursive call. It is calling itself here. Then what all the processing it has to do, it is doing it afterwards, after the recursive call. So there is no statement, no operation before the function call. See, if there is something here, then it is not a head recursion, right? If something is there before the function call, just it is a recursion. We don't have to give any special name for that one. So there is nothing before that one, then we can say this is a head recursion. So what do you mean by head recursion? It means the function doesn't have to process or perform any operation at the time of calling. It has to do everything only at the time of returning. So all the processing is done at returning time. Then such functions are head recursion. So the example of this type of recursion already we have seen in the previous video. This was the simple example. So you can see that the function is first calling itself, then the second statement it is printing. So the printing will be done at returning time. So the function doesn't do anything at calling time. So such recursions are head recursion. Next, we will compare head recursion versus loop. Can we convert them into loop? Let us discuss this. I will try to write the same function using loop. So let me write here void function fun. Now, instead of conditional statement, I have to write a loop that I already have shown you. So, if n greater than 0. Now, here first it has to make a recursive call, then it is printing. So, if you remember the output of this one, the output of this function was 1, 2, 3. As it's going to print at returning time. So if you remember the answer in the previous video, or else you can check back, the result of this type of function is 1, 2, 3, because it is printing at returning time. Now, as it is, I have tried to write the function with a loop. Now, I want the output to be 1, 2, 3. So if I use printf here, printf %d n, then if I am passing function fun with value 3, then first value of n will be 3. So 3 is greater than 0, yes. So it will print what? 3. It will not print 1. First value that will be printed will be 3. It is not 1. Then if I have to repeat, then just like this one, instead of that if I write n minus minus, then it doesn't work same as that one. So you cannot easily convert it. So you have to write it in some other way to get the same output. But as it is, looking at the function, if you try to convert, it's not easy. We can write some function which prints 1, 2, 3 using loop, but looking at this function, we cannot directly create it. So it means I have to write it in a different way. So let me write it. Suppose I have to take some variable I, and that is value 1. Then I should say I is less than equal to n. Then here I should say I plus plus, and I should make this I plus plus after printf. So let us try to run and see this one. If I pass the value as a 3, that is n is a 3. So I is 1, 1 is less than 3, so it will print I, that is 1. So output is 1. Then I becomes 2, so 2 is less than 3, so it will print 2, so result is 2. Then I plus plus, I becomes 3, so 3 is less than equal to 3, so I is 3, so it will print 3. Then I plus plus, I becomes 4, 4 is not less than equal to 3, so it will not enter in, and it will finish the loop and it will come out. So the output is 1, 2, 3. So that's it. You can see that that function cannot be as it is converted. So head recursions, or if a recursive function has to do something at returning time, it cannot be easily converted in the form of a loop, but it can be converted. It doesn't look as it is. So that's all about head and tail recursion. In the next video, we will see tree recursions. In this video, we'll learn about tree recursion. So first of all, I will compare what is linear recursion and tree recursion. Let us see. See, a linear recursion, a function that is a recursive function, if it is calling itself only one time, you can see that the function is calling itself only one time, then it is a linear recursion. So already we have seen in the previous video that the functions which are calling just one time, and we have seen head recursion and tail recursion, but in this example it is having something to process before the call as well as after the call, so it is just a recursive function, right? We cannot name it as head or tail recursion. And this code is not a C or C++ code. I have just written a pseudo code here, so it's not a complete function like now integer, everything is not there. So don't try to read it as C language code. Just I am showing you structure. Then here, tree recursion. So what is tree recursion? If a function that is recursive function is calling itself more than one time. So here you can see it is calling itself first time, and here it is calling itself second time. So if a recursive function is calling itself more than one time, then it is tree recursion. So in my example, I have shown it as 2 times. So it may be more than 2 times also. So that we call it as tree recursion. So here I have one example of tree recursion which is similar to the previous examples, only the difference it is calling itself more than one time. So I will trace this one and show you how it will work and what will be the output, and also I will show you how the stack is created in this one. Let us look at the tracing of this function. The function is called by passing value 3. I have taken a piece of stack. I'm not taking complete memory, entire memory, just I am showing you stack, how it is used by this recursive function, which is a tree recursion. Let us trace. First, it is called by passing function with value 3. So the first call is fun of 3. For this function, an activation record is created and the value of n will be 3. So this is the first record created. Then what are the steps it has to perform? First print the value, then make 2 calls. So it will print the value, then it will make 2 calls. Let us print the value. See, it will print the value 3 and make first function call fun for n minus 1, that is 2. And second call it has to make, that it will be doing once this call has finished. So let us first finish first call. So for this call, and again activation record is created where the value of n will be 2. Now for this call, let us see what happens. N, that is 2, is greater than 0. Yes, 2 is greater than 0. Print and then make 2 calls. So let us do it. Print 2 and make 1 call with n minus 1, that is n minus 1. So 2 minus 1, 1. Then second call it will make after finishing this one. So far we have 2 values printed. So I'll also be writing the output here. So the output of the function so far is 3 and 2. Now let us continue with this call. This call, again an activation record is created and the value of n will be 1. Now for the value of n is 1, 1 is greater than 0. Yes, it is greater than 0. Then it will perform 3 steps. First print 1, then make 2 calls. So first it will print the value that is 1. Then it will make first call with reduced value of n. So this is 1, so it will be 0. And second call it will make afterwards. So for this call, again a fresh call is made from here. So a new activation record is created where the value of n will be 0. Now this time fun of 0, this is 0, 0 greater than 0, no. So it will not enter inside and it will not perform these steps. So the function call terminates. Now the function calls terminates. This activation record is deleted from the stack. So before deletion, if you count 1, 2, 3, 4, 4 activation records. How many calls? 1, 2, 3, 4. 4 calls. So 4 activation records are there. So this is deleted. Now once it is deleted, it will go back to the previous call. It means this has finished. It will go back to the previous call. In previous call, for performing 3 steps, first was completed, second is also completed just now, third one has to be performed. So it will make a call here for n minus 1. Next call, n minus 1. So n minus 1, 1 minus 1 is again 0. So again it will make a call with value of n as 0. So again the activation record is created. Actually this was gone. So new activation record is again created. So I have erased this one. So let us assume again it is created here. So now again the size of the stack is 4. Next, for fun of 0, this is 0. 0 is not greater than 0. So it's not going to enter inside. Function ends. So this activation record is deleted and this function terminates. So now you can see that for fun of 1, all 3 steps are completed. Printing, calling itself 2 times with reduced value of n. That is 1 is printed and 0, 0 is called and they have finished. And in the output we also have 1. Now this call is completed. All 3 steps are over. So it will go back to the previous call. So go back to the previous call means this call has finished, means this activation record is deleted. So right now there are only 2 activation records in the stack. One is for value of n as 3 and value of n as 2. Now it is back on this call where n is 2. And in that, out of 3 steps, it has already performed first step, printing of 2 and call. Then the next, again it has to make a call, that is n minus 1. So now it will make a call for fun of n minus 1. So again fun of n minus 1, that is 2 minus 1, that is 1. Now again a fresh call. So new activation record is created. Now for this it is 1, so it will print 1. Now all these things that happens will be similar to this one. So it means it will print 1 and then it will call itself for, now I will not write complete name fun, I am just using f because of lack of space. F of 0, so this activation record is created again. Then this ends, so this is deleted, then goes back, again call for 0. So again an activation record is created for 0 and this ends and this is deleted. Now control goes back to this is finished, goes back to this, all 3 steps are finished, then goes back to fun of 3. In this it has to perform one more step, that is fun of, this was 2, so this is also 2. So 3 minus 1, 3 minus 1. So again 2 calls are made. So already this portion we have seen it completely. Same thing happens here also. Here also same thing happens. Now this I have taken enough space for explaining this one. Now this I have to write it in small size, but it will happen as it is what has happened here. So let me finish it quickly. So the first thing happened is value 2 is printed. 2 is printed. And here activation record is created. Then call for fun of 1. New activation record for, this was gone, sorry. So 1 is created. Then for this value 1 is printed. Value 1 is printed. Then call for fun of 0 and this ends. Activation record one more is created with value 0 and this ends. And again a call for fun of 0. Again and 0 and this also ends. This also goes back. Here fun of 1. For this 1 is printed. So output is 1. Then call for fun of 0, call for fun of 0, right? So again 2 more activation records, then that also finished, this also finished, and finally 3 also finish. So this is the output that we get. So I have simultaneously shown you how the activation record works. So you can see that maximum size of the stack was how much? 1, 2, 3, 4. Maximum was 4. 1, 2, 3, 4. And total how many activation records are created? As many calls are there, right? I did not draw all, just I have given the idea. I did not draw each and every call here. So if I count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So total 15 calls are there. So 15 times activation records are created and deleted. Now I will remove this stack and redraw this tree once again, and we will analyze more on the tree. I have redrawn the tree once again. Let us analyze the tree, so by which we can analyze the working of this recursive function. So here is a tree. Now first of all, let me label the calls in which order they are called. See, the first function call is this one, 1. Then second call. This will be done once this has finished. It has to finish. So under that there are 3 things again. So second call, printing is done. Then third call. Then this one will be done once this has finished. So under this, printing. Then this call, fourth call. Now this is fun with value 0. This will terminate. Then it will go to this call. So this is fifth one, fifth call. Then as this has finished, it will go back and then it will make this call. So this is sixth call. Then under this, 7th and 8th. Now these are also finished. So under this, if you see, all the calls are completed. Now it will go to this one. So this is the 9th call. So that is the 9th call. ninth activation record to be created in the stack. Now height is how much? 1, 2. So only 2 will be there in the stack. But the count, if you take this, the ninth one. So this is ninth call. Then under this, printing is done and this call is made. So this is the 10th call, and then printing is done and this is made 11th call, and this will finish now because value of n is 0. Then this call 12th call. So this is also finished because the value is 0. So this will also complete. All three steps are completed under this one, 12th call. Then go back for this one, right side. 13th call, then 14th call and 15th call. So that's what already I have counted them. So total 15 calls are made in this particular function when we pass the value as a 3. So I have shown you the order in which the calls are made. This is very important for you to visualize or trace how these type of functions work, which are calling themselves more than one time. Now we will analyze the time complexity. So time complexity depends on the number of calls. Yes, in each call it is printing, except in the calls where the value is 0. So otherwise it is printing almost for every call. Then now let us see how many calls are made if the value is 3. So for n, how many calls will be made? With that we can decide the time complexity of this one. So let us analyze this one. So if I count the number of calls level wise, then in this level just one call is made, and in this level if I see 2 calls are made, 2, and in this level 1, 2, 3, 4 calls are made, 4, and this level 1, 2, 3, 4, 5, 6, 7, 8 calls are made. So it means when I have passed the value as a 3, then in the first level 1 call, next level 2 call, next level 4, then next 8. For 3 there are 4 levels, and if the value of n that I am passing here, this value n, if it is 4, then there will be 5 levels. It means the tree will be more bigger than this one. Then how many calls it may be having? So let us analyze this one. So for any value of n, how many calls it will be? So let us sum up all these. So I will take the sum of all those. 1 plus 2 plus 4 plus 8. This is total 15. Yes, we know this. Count all of them, that is 15, or you have add all these, you get 15. So this is nothing but 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3. So this is nothing but sum of the terms of, that is summation of terms of series, that is GP series, that is sum of geometric progression terms. What is all that GP series and all, we will learn some other time, but right now I'll just write on the formula. So this will be nothing but 2 power, highest term is 3, so this is 3 plus 1 minus 1. So it means if I have 2 power 0 plus 2 power 1 plus 2 power 2 goes on to, if this is n, then this will go till 2 power n. Then how much that is? This is 2 power n plus 1 minus 1. So that many calls it will make. So what is that equal to? So this is order of 2 power n. So total 2 power n calls are made. So if I substitute the value of 3 here, so 2 power 3 plus 1, 4. 2 power 4 minus 1, that is 16 minus 1 is 15. So for any value of n, the number of calls will be order of 2 power n. So that's all. We have seen what is tree recursion, and we have taken one example, and we have seen how the tracing tree is generated and how the calls are made, how the stack is used, and what is the time complexity. So for this example function, it was 2 power n. So it depends on the function what time complexity you may be getting. It's not that every tree recursion will have 2 power n. For this function, it is 2 power n. So the time is order of 2 power n. Then what is the space? What is the space complexity? So it depends on what is the maximum height of the stack, because total activation records depends on number of calls. but how much space it was occupying inside the stack. So you have observed that same space was reused inside the stack. One activation record was gone and the same place another activation record was created. So we don't require much space, just like 2 power n, but we require the space equal to the height of a tree that we got here. So 1, 2, 3, 4. If it is 3, 4 is the space. So if it is n, n plus 1 will be the space. So it is order of n. Space complexity is order of n. So maximum stack size that we need is n. That will be sufficient. So that's all about tree recursion. Let us look at tree recursion. For that I will create a new project. Project type is command line tool. Project name I will give it as tree recursion. Next, create the project. Your project is ready, and here is the main function. Here I will write down a function for tree recursion, the one we have already discussed. Function fun, which takes parameter n. If n is greater than 0, then printf the value of n. Next, it will call itself by passing n minus 1 for 2 times. Now this function I will call it from main. Function fun by passing value 3. Let us run the program. See, the output is 3211 211. Here is the output 3211 211. So the same output we got. Now let us debug this program and check how these functions are called and how this output is generated. So I'll put a breakpoint here and I will run the program. So debugger stops here at the breakpoint and at the beginning point of the function call. Inside debug navigator we can see just main function. Now here we will observe how the function calls are created and destroyed. You can better watch in this watch window how these function calls are created and how the value of n are changing. So let me continue. The first function call, you can see here that n is 3. Inside watch n is 3. Printf, it will print 3, then it will call itself for 2. Now this time n is 2 and there are 2 function calls here in the debug navigation. Printf2, then call itself for function 1, then printf1, then call itself for 0. This time it will not execute. So total 4 calls. This is for 3, 2, 1 and 0. From the bottom if we check, don't go on these numbers. These are actually the ordering, that is 0th call, first call, second call, so on. This is not the values of n. Now this function ends and it will go back to previous call where the value of n was 1. Then it will make a second call. Now you can see that it is on the second line. The second line is highlighted with green color. It's going to execute the second call. Now the value of n is 1. So again 1 minus 1, 0. Yes, the function call is for 0. Here you can see in the watch window value is 0. And again the function calls are 4. This function will not enter into if, it will come out. Then it will go back to function call for 1. Then back on 2. Now for 2, first call has finished. Now it is going to make second call for 1. N value is 2. Now for 1, 1 is printed once again. So here we got the output. Then for 0, again 0, 2 calls are over. Now back to 2, and back to 3. Now for 3, when the n value was 3, this first call has finished. Now the second call will be done, so it will be 3 minus 1, 2. So same thing, just how we got a 2, 1, 1, same way we get a 2, 1, 1. Now you can see here inside the debug navigation, that is main function, and only one function is there with the value of n as 3. Now again it will expand, it will be ascending. Print a 2, call for 1, print 1, call for 0. Now again you can see that here 4 function calls are there above main. This ends and 0 also ends. 1 is printed, 0 is called, 0 terminates, 2 terminates, and 3 terminates. It's returned back to main function. So the things to observe here are how many activation records are created inside the stack. If you count total calls are 15, but at most at a time maximum 4 calls were there. So that's all about this tree recursion. Now let us look at indirect recursion. In indirect recursion, there may be more than one function and they are calling one another in a circular fashion. So that if the first function calls second one and the second call third one and the third one again call back first function, then it becomes a cycle, so it becomes a recursion. Like suppose there is a function A and the function A is calling function B and the function B is calling function C and C is calling A again. So instead of a function calling itself, here function calling another function and is calling another function, and that C is calling A, so it becoming a cycle, so it becomes a recursion. So here I have a skeleton for showing you indirect recursion. Here is function A. Function A is having some condition, and if condition is satisfied, it is calling function B. And the function B, there is some condition, if it is satisfied, it is calling function A. So from here it is calling B and then B is calling A, so it becomes an indirect recursion. Here B is called with reduced value of n and again A is called with some more reduced values of n. So they are calling each other. At one point they may stop if the condition fails. If any one function stops, then it will return back to the first starting call. To explain how this works, I have set of functions as an example here. These are in indirect recursion. So let me trace this with an example and show you. Let us trace this example. So first of all, I will read it out. See, this is a function A and taking parameter n. If n is greater than 0, then it is printing and then calling function B by passing n minus 1. This function B, if n is greater than 1, then it is printing and calling function A by passing n by 2. So I'll start this by calling function A first. Let us say function A is called for value 20. Let us trace this one. Function A is taking 20 as parameter, 20 is greater than 0. Then it has to perform two things, that are print the value and call function B by passing n minus 1. So function A will be calling B by passing n minus 1. So the first thing, it will print 20 and it will call function B by passing 19. Now what function B does? Function B, if n is greater than 1, then it will print and call function A by passing n by 2. So two steps are there. First print and then call function A by half of n. So this is function B, so it will print 19 and it will call function A by passing 19 by 2, 9. Now again control goes back to function A. Function A takes the argument and we know well that it's printing and calling B. So prints 9 and call B by passing n minus 1, that is 9 minus 1, that is 8. Now it is back on function B. Function B, print and call A by half of this one. So print 8 and call fun of A by passing half of 8, that is n by 2 of 8, so it is 4. Now again function A prints and call B, prints 4 and call B by passing 4 minus 1, that is 3. Now function B, n is greater than 1, yes 3 is greater than 1, print and call function A. So 3 is printed and call function A by passing 1. That is 3 by 2. That is integer division. We are doing integer division here. Now A, it will print 1 and call B, function B, by passing 0. Now function B, when n is greater than 0, it works, otherwise it stops because n is 0 now, so it will not enter inside, it will terminate. Once the function terminates, it goes back to function A, then B, then A, then B, then B, A, then B, then A. So it goes back and reaches the starting point and the function calls ends. The output will be 20, 19, 9, 8, 4, 3 and 1. So that's all about indirect recursion. I have just taken a sample program to demonstrate how indirect recursion works and what does it mean. Now in this video we will write a program for indirect recursion that we have already discussed in previous video. So we'll have a demonstration of that indirect recursion. So for indirect recursion I will create a project, but this time I'll give the project name as recursion. All other demos I will do in the same project. I will not be creating project every time. I will just delete and write down the fresh code. But the project will remain same, so the name I have given as recursion. Already you have seen how to create a project, so I will utilize the same project for all other demos. Create a project for recursion. Here is the main function. I'll remove this. So here I will write on two functions. Function A, which takes parameter n, if n is greater than 0, printf n, and call function B for value n minus 1. Next I should write on function B. Function B, it takes parameter n. If n is greater than 1, then printf value of n, and then call function A by passing n by 2. Now here I am getting an error saying that this function B is not defined before it is used. It is used here in function A. So if you read the code from here line by line, then first we are coming across a call to function B, then later on we are having a definition of function B. So this function B should be defined before it is used. So here I will write on the prototype of function B. So error is gone. So before using a function, it must be either declared or defined. So definition we have written here. So that's why we have to write declaration so that we can call it at this place. Now these functions we have called them by passing value 20. Let us run the program and see what the output we get. If you remember the output is 20, 19, 9, 8, 4, 3 and 1. So we have already seen it's working. I have explained you everything. So just for the demonstration, I have written the program. So I got the result. So that's all with the indirect recursion. Let us look at nested recursion. In a nested recursion, a recursive function will pass parameter as a recursive call. See, here is a recursive function and it is calling itself, so it is recursive. It is calling itself here. But what the parameter is? Parameter itself is a recursive call. Means unless the result of this recursive call is obtained, this call cannot be made. So a recursive call is taking a recursive call as a parameter. So this is recursion inside recursion. So it is called as nested recursion. So for as an example, I have one function here. I will trace that function and show you. Here is a nested recursive function example. Let me read it out first. a function which is taking parameter n, and if n is greater than 100, then directly it is returning some value. If not, then it is making a nested recursive call. So function call is again taking a parameter as function call with some increased value of n. So for tracing this one, I will take the value that is 95, and let us try this 95 on this one. So I will trace this function for this value. So let us start. First function call fun of 95. 95 is greater than 100? No. Then it will enter into else part. So in else, it will call itself again by passing fun, and again fun of 95 plus 11, that is 106. So first of all, I should know the result of this one. Then I can use that value as a parameter for this function call. Let me evaluate this one first. See, fun of this is 106. So fun of 106. Let us check this call. Fun of 106. 106 is greater than 100. So it returns 106 minus 10, that is 96. So the result of this function is 96. So this 96 is the result of this function call. So this has to be placed here. So it becomes function of 96. So actually we started with 95, then the next call is nothing but 96. Now for 96, 96 is not greater than 100, so it enters into this else part. Then it will make a function call with again nested function call with what is the value of n plus 11. So it is 96, 96 plus 11 is 107. So directly I am writing the value. So I should know what is the result of this fun of 107. So let us find out fun of 107 here. Fun of 107. When this is fast, n is 107. So 107 is greater than 100. So it returns 107 minus 10. So this becomes 97. So this is the result of this function call. So actually this function becomes now fun of 97. Now let us solve this fun of 97. 97 is not greater than 100, so it will enter into the else part and it will make the function calls, that is fun of n plus 11, that is 97 plus 11, so this becomes 108. Now as we have already seen these two calls, see this was 106, so it becomes 96. 107 became 97, so 108 will become 98. Instead of tracing it, I will directly write down this result. So this is 98. So fun of 108 is 98. So this function call becomes actually fun of 98. Now fun of 98, 98 is not greater than 100, so it enters into the else part. Then it becomes fun of 98 plus 11. So this becomes 109. And this function 109, this becomes fun of 109 becomes 99. So this is fun of 99. Fun of 99 is not greater than 100, so it will go into the else part. So fun of 99 plus 11. So this becomes 110. Now what is the result of 110? Fun of 110 will be 100. Here it enters into the if part and returns minus 10. So this is 100. So this call becomes fun of 100. Now fun of 100 is not greater than 100, so it will enter into this part. So I have to continue here. I will continue here. So this becomes fun of 100 plus 11. So this is 111. Now fun of 111, this is greater than 100. So this is 111 minus 10. So this becomes 101. So this function call, finally, it becomes fun of 101. Fun of 101, again it is greater than 100, so this will be 101 minus 10, so this becomes 91. Now this time it will not enter into the else part and it will return 91. It goes back to this call and goes back to this one and this one and this one and this one. Finally, the result of this one is 91. So that's how I have taken one simple example to show nested recursion. Usually nested recursion, if you want to trace them, they expand like anything. It will become a big tree. So here you have observed that for every nested call, first of all, we should know the result of this one, and that result is utilized with this function call. Like here I have written fun of 96. Then again, there's a nested call. Then I should know the result of this one, that is 97, and I use that 97 here with fun of 97. So every time you have to find out the result of nested or inner call, then you can make a outer call. You can find out the result of outer call. So that's all with nested recursion. We will see more examples on recursions in coming videos. In this video, we'll look at the demonstration for nested recursion. The project is ready. I am using the same project, and here I will write on the code for nested recursion. I will write on the function that we have already seen. Function takes parameter as n, and if n is greater than 100, it will return n minus 10. Otherwise, function will return function of n plus 11. So this is a nested call. Then from the main function, I will take some temporary variable r. Then in r, I will assign the result of the function call by passing 95, the value that we have seen. Then here I will print the result of r. New line r. That's it. It's a simple function. The same result we get, we know the result, that if 95 is passed, what is the output? So let us run the program and see the result. 91 is the result. Yes, already we have traced this program and we have seen it. If I pass the value 99, let us see what will be the result. Still 91. If I pass the result as 100, then let us see what is the result. Still 91. If I pass 200, 190. See, if n is greater than 0, it is just returning n minus 10. So what is the value of n is minus 10. Otherwise, these calls are made. If I pass the value 30, then let us see what is the result. So again, answer is 91. So this 30, the value 30 will grow up to the value 101, and then from 101, when 10 is subtracted, it gives 91. So for any value, this function is going to return value 91. So you can debug this function and check. So I am not debugging now. Already I have shown you how to debug the program. So whichever editor you are using, you can try debugger. That will help you clearly understand the flow or the working of program. So that's all in this video. Now let us look at an example recursive function for finding sum of first n natural number. So first of all, I'll explain you what does it mean by sum of first n natural number. Then I will devise a recursive function. Then we will write a recursive procedure, that is function, using C or C++ language. Let us understand what does it mean by sum of first n natural numbers. So if I take some natural numbers like 1, 2, 3, 4, 5, 6, 7. Suppose I want to take up to 7, then I want the sum of all these. Summation of first n natural number. So how many natural number? First 7. So first 7 means 1 to 7. Now same way, if I say first n natural numbers, then it is 1 plus 2 plus 3 plus 4 plus goes on to last term is n. N can be anything. Like in this previous example, it was 7. It can be anything. Now for this summation, let us write a recursive definition. So for recursive definition, I will say sum of n terms is 1 plus 2 plus 3 plus 4 plus goes on to, now before nth term there will be n minus 1, then n. So I have included one more second last term, I am showing it. Now if I take the summation till here, this is nothing but sum of n terms is sum of, this is n minus 1 terms. See, n terms means 1 to n, then n minus term will be from 1 to n minus 1. Then 1 to n minus 1 will be from here to here, that is till this point, Then what more is remaining? Plus n. Then if I add n to that, it gives me up to n. So this became a recursive definition. Now this I can write it like this. Sum of n terms can be defined as sum of n minus 1 plus n if n is greater than 0. If n is equals to 0, then it's not a natural number. Natural number starts from 1 onward. So n is 0, so let us say answer is 0. See, remember, whenever you define any recurrence relation or recursive function, then you must have two type of statements. One is for the large value of n, what is the formula? Then for the small value of n, what is the answer? So usually for small value, we give a direct answer. So if n is equals to 0, there is no formula, direct value is there. So based on the same thing, I can write a recursive function in C or C++. Let us say int sum, which takes integer parameter n, and if n is equals to 0, return 0. Otherwise, return sum of n minus 1 plus n. So here what I want to explain you here is, if you have a recursive definition of any problem, then directly you can convert into a recursive function in any programming language which supports recursion. So in C, C++, you have recursion, so you can directly convert this one. See, if sum of n, and if n is equals to 0, return 0. If n is equals to 0, return 0. Otherwise, if n is greater than 0, then return sum of n minus 1 plus n. So sum of n minus 1 plus n. So that's it. That is a recursive function for finding sum of first and natural number. Now finally, I have one more thing to show you, that for finding the sum of first and natural number, there is a direct formula, that is n into n plus 1 by 2. So this is the formula. So it means I don't have to write a function for that one. Function will consume time, and it's a recursive function, and it will take time for making number of calls. Instead of that, I can simply use a formula and write a program. So usually we write just a formula whenever we have to find out sum of first and natural number instead of writing a function. But for experiencing or learning recursive functions, I have taken this example. Even the same function, we can write it using iteration, that is using loop. Recursion will be costly because it uses stack internally. So I will write down two more versions of the same function. Instead of recursion, I will use loop, and also I will directly use the formula and show you. So I will remove this definition, then I will write down two more functions. Here I have a function for sum which is directly using the formula. If you pass the value n, then it will take the formula. Using the formula, it evaluates n into n plus 1 by 2 and returns the result. So this is the simplest function, and it will take very less time. It is just constant time because just it has to evaluate a simple expression. So I can say that the time taken by this function will be constant. Few number of operations like 1 operation, 2 operation, and 3 operations. So total it may be performing 3 operations, that is constant. So this is the fastest method. This is using formula. Now here I have a function for finding the sum of first and natural number using loop. Now this function, it takes the value of n and it will start I from 1 to n. So I will start the values from 1 to n. Initially s is 0, so this I value from 1 to n will be keep on added to that s. So first time 1 is added, the next time I becomes 2 and 2 is added, then 3 is added, then 4, up to n all numbers are added, and this is returned. So this is using loop. I have written the function. If I find the time complexity of this function, so one of the major important statement is this one, and this statement is repeating for n times, as I is taking the values from 1 to n, so this will be repeated for n times. This is statement one time only, and this is statement one time. And if I consider for loop, mostly it is written as n plus 1 time. So the main statement is this one. So this is executing for n times. So I should say that the time taken by this algorithm is order of n. Time taken is order of n. I have found out the frequency of execution of each statement, and the main statement is this one where the addition is done, and that's going to execute for n time. So our focus is on that statement, this order of n time. And how much memory it takes? Just 3 variables are there, that is I, S and N, that is passed as parameter. Only 3 variables are there. But what about recursive function? A recursive function internally uses stack. Whatever the value of n we pass to that, it will make those many calls and it will create those many activation records. So it's having just one variable n, so that n variable will be created many times, as many times, depend on the value that you are passing. So it takes more space, but the time will be order of n only. So let me trace this function and show you for the value 5. If I call this function sum for value 5, then what it will do? If I pass 5 is not 0, then it will call sum of n minus 1 plus n. So it will call itself for sum of 4, and the value of n is what? 5, that is added. So it's making one more call. Then in this call, again the same thing, it's not 0, so it will make a call for sum of 3 and then also add 4. Then it will make a call for sum of 2 and also add 3. Then sum of 1 and also add 2. Then sum of 0 and also add 1. Now finally, sum of 0, as it is 0, it returns 0. So this is 0. So 0 plus 1 is 1. And this is returned here. So this is 1 plus 2, that is 3. So 3 is returned here. So this is 3 plus 3, that is 6. 6 is returned here. So 6 plus 4 is 10. 10 is returned here. So 10 plus 5 is 15. 15 is returned here. So the result is 15. So while returning, the addition is done, and you can see that how many calls it has made. For 5, it has made total 6 calls. So the size of the stack is 6, and the variable n is created for 6 times. So memory is more. But how much time it is taking? There are total 6 calls. So for value of 5, there are 6 calls. So for value of n, there will be n plus 1 call. So it is order of n. So the time taken by this function is order of n. But space is also 6 times for the value of 5. So the space is also n plus 1. So space is also n plus 1 here. This is time. So there, recursion is costly, but it was easy for converting a mathematical definition, that is recursive definition, into a function. That's how recursions are easy to write compared to loops. For loop, we have to devise some logic, work on the problem, understand the problem, devise some logic. Then it may work faster compared to recursion, and it takes less space compared to recursion. So mostly in our applications, in our program, we write loops only instead of using recursions. But actually, the problems are solved using recursions in mathematics. So I have taken a very simple example and I have shown you how we can define a recursive function for finding sum of first and natural numbers. Now in the coming videos, we'll see more examples of recursions. In this video, I will show you a recursive function for finding sum, and also I will write a iterative version of sum of first and natural numbers. So let us write the program that we have discussed in a previous video. I will write a function for finding sum of first and natural number using recursion. Int sum, which takes parameter n and returns an integer. If n value is 0, return 0, otherwise return sum of n minus 1 plus n. So this is the function that we have already seen. So directly I have written that function. Now here inside the main function, let us take a variable r for getting the result of that function sum, and I will pass the value 5. Then I will print this result. That's it. A function is ready, a recursive function. A function is very small because it is recursively defined. I will run the program and show you. The result we know it should be 15. So yes, the result we got it as 15. You can debug this function and check it. Already I have shown you how to debug it. So you can see how many function calls are made and how the values of n are changing. Now we'll write a function isum, that is for iterative sum of first and natural numbers. So here I will take a temporary variable s and also I. S is initialized to 0, in which I will store the sum of all the numbers. I starts from 1, I is less than or equal to n. So this is a for loop, I plus plus, sum assign sum plus I every time. So I will be taking the values 1 through n and all those values are added to sum. Then finally return sum, that is s, variable s. Inside the main function, instead of recursive sum, I will call iterative sum, isum. Then let us see. Now I will run the program. We should get the output 15. Yes, again we got 15. So the result is same whether a function is recursive or iterative. Let us debug this function and check how the iterative function is working, how this loop is working. I will put a breakpoint here on the function call inside main, then I will run the program. So it has stopped at this function call. I will continue execution, it will enter into isum. Now it has entered into isum. Now you have to look at this window where the value of n is 5 and s is 0 in this inside this function. So we have variables n, s and I. So you have to look at the values of these three variables here inside the window. See how they are changing in a loop. Now I is also 0. So it is upon the for loop now. It is upon the for loop. Now I am continuing. I is 0. Then this I will be added to s. Here I will be added to s. So s also became 1. So inside the watch you can see that s has become 1. Then continue, I became 2. Just keep watching here. Then 2 is added to s, so s became 3. Then I became 3, 3 is added, so s becomes 6. Then I becomes 4, 4 is added, so s becomes 10. Then I becomes 5, 5 is added to s, then s becomes 15. And I becomes 6, so it terminates for loop, then it will return the result. So that result is in R now. Now R is 15, so 15 is printed. So we have observed how this for loop is repeatedly executing and generating sum of first and natural numbers. So both the functions are for same purpose, but the approach of solving a problem or writing a function is different. This is recursive and this is iterative. So that's all in this video. Now let us discuss the problem finding factorial of a given number. So for this also we can define a recursive function, and even using iteration, that is using loop also we can write it. Let us first of all devise a recursive function for this one. So first I will define what does it mean by factorial of a number. See, factorial is represented with this symbol. So this means factorial of n means 1 into 2 into 3 into goes on to n. So it means factorial of 5 is 1 into 2 into 3 into 4 and multiplied by 5. So this will be 120. If I multiply all these things, I'll get the answer 120. So for n, I have to continue up to n. So for 5, I continue till 5. For 10, I should continue till 10. So just like sum of first and natural numbers, this is multiplication of first and natural numbers. That is called as factorial. And even I'll tell you one more thing, that 0 factorial is also possible and its answer is 1. So even 1 factorial is also 1 and 0 factorial is also 1. So both the results are 1. Now let us define this recursively. If I say fact of a number n is 1 into 2 into 3 goes on up to one more term I will include, that is one more number, n minus 1 into n. So in this, if I observe factorial of a number from 1 to n, this portion if I take, this is factorial of n minus 1. Yes, this can be written as factorial of n minus 1. So factorial of n is a factorial of n minus 1 multiplied by n. If I multiply that with n, then I get the result, that is factorial of n. So this can be defined recursively. Factorial of any number n is factorial of n minus 1 multiplied by n when n is greater than 0. When n is equals to 0, means for 0 also answer is 1. So return 1. That's it. So this is the recursive definition. And once you have a recursive relation or mathematical formula, then directly you can convert that recursive formula into a C++ function. So let me write down a function for this one. Integer factorial of n. If n is equals to 0, return, when it is 0, return 1. Return 1. Else, return this one. So return factorial of n minus 1 into n. So the function, writing a recursive function is so easy, you can directly convert a formula into recursive function. Now same function even we can write using iteration, that is a loop, right? And this is using recursion. Now it is more similar to sum of first and natural number. If you remember in the previous example, we saw a similar function, only the difference was here it was plus, and one more difference, return 0 was there instead of 1, because the multiplication is there, so it should be 1. So the function is similar. Now if we do analysis, the analysis will be same. The size of the memory required depends on the value that you're passing. If you find function of 5, that is factorial of 5, then it will be making 6 calls. So the height of the stack will be 6. So the amount of memory consumed is order of n, and the time, number of calls depends on the value that you're passing. Like for 5, it will be making 6 calls. So again, it is order of n. Just in the previous video for finding sum of first and natural number, we have done similar analysis. So I want to avoid analysis here because already we have done analysis for this one. So analysis is same. Now writing a iterative function for this one is a student exercise. So you can write on the function by yourself. So that's all about a factorial of a given number. In this video, we will see a function for finding factorial of a number. I will show you recursive function as well as iterative function. So first let us write recursive function for finding factorial. Function takes parameter n. If n is equals to 0, then return 1. Else return factorial of n minus 1 with n. Inside main function, I will take a variable r to get the result of that factorial function. Let us find the factorial of number 5. The answer is 120. We already know the answer. We should get the same result. Display r. I will run the program. We should get the output 120. Yes, the output is 120. It's a factorial of 5. Let us check factorial of 4. It should be 24. Yes, it is correct. Let us check factorial of 0. What the result will be. It is 1. Let us use a negative number here and see what the function will do. Factorial of minus 1. See, when the value of n is minus 1, then it is not 0. So it will be calling itself again and again, minus 1, so it's minus 2, then minus 3, minus 4, goes on. So actually it has gone into infinite calling and terminated. So you can see total how many calls it has done. 262054 calls it has done. Then why did it stop? Because of stack overflow. So if a recursive function is going into infinite recursive call, so at one point it will terminate because of stack overflow. System stack has overflown, so it has made so many calls. Factorial is not defined for negative numbers. So if you want to avoid this recursive call, so then here you can write a condition to stop the function if the number is negative. Now I will write an iterative version of factorial. I will call it as ifact. It takes a parameter, and for finding factorial I will take f, that is initialized with 1, and also we need a variable I for iteration. Using for loop, I assign 1 onwards and I less than or equal to n, I plus plus. Then factorial is multiplied by I. So I will be taking different values from 1 to n, and it will be getting multiplied by f every time. So this will be multiplying just like 1 into 2 into 3 into so on to n. Then finally return f. F is having the result. And here inside main function I will call this I factorial function, and I will pass the parameter as 5. Let us run the program and see what the output will be. It should give output 120. Yes, output is 120. Let us debug the program quickly and see how the values of f and I are changing in this iterative version. So you can observe this watch here. Watch this portion where the values of fi will be changing. I will continue execution. It will enter into factorial function. Now the variables I and f both are there. I is 1, so 1 multiplied by f, f is also 1. Then I becomes 2, multiplied by f, f becomes 2. Then I becomes 3, multiplied by f, f becomes 6. Then I is 4, 4 is multiplied 24. I is 5, 5 is multiplied 120. I becomes 6, then it will stop. And come back to main function and print the result. So end of program. So that's all in this video. We have seen recursive as well as iterative version of factorial function. In this video we'll talk about exponent function, that is m power n. So raising m for n times, that is multiplying m for n times. So for this problem we will try to define a recursive function. For that, first of all, I will explain what the problem is. See, suppose I have to find out 2 power 5. So this means 2 into 2 multiplied by 2, and this is multiplied by itself for 5 times. So it means m power n means m should be multiplied for n times, m should be multiplied for n times. Now this, if I write it as a power function, that is power m comma n, then it means m into m into m, that goes on to n minus 1 times into 1 more time. This will continue for n minus 1 times and 1 more time. For example, 2 power 5, see this is 4 times, this is 4 times and 1 more time. So same way, m power n means m should be multiplied for n minus 1 times, then again multiplied by 1 more time. So it becomes total n times. Now this I can define it recursively. I can say power of mn is power of m comma n minus 1 times into m. So yes, this can be defined as a recurrence relation power of m comma n minus 1 into m when n is greater than 0. When n has become 0, then when n is equals to 0, as it is a product, so it should return 1. So minimum value is 1. So that's it. So for this mathematical definition, I can write a recursive function using C or C++. So let me write a function here. Integer par int m comma int n. If n is equals to 0, return 1. Otherwise, return par of m comma n minus 1. So that's all. It is just a 2-3 line functions. It's a simple function. So this is converted into a recursive function. I will take one example and show you how it works. Let us trace this one for power of 2 raised to 9. So 2 raised to 9, m value is 2 and n value is 9. So 9, that is not equal to 0. So it should perform this operation. That is power of 2 comma n minus 1. That is 9 minus 1. That is 8. So I will rewrite it as 8 multiplied by m. So what is m? This is 2. So that's it. Continue. Now this call has to be finished, then only multiplication will be done. So what this call is? Power of 2 comma, as this is 8, it is not 0. So every time this has to be done. So this will become 7 multiplied by 2. Then again power of 2 comma 6 multiplied by 2. And power of 2 comma 5 multiplied by 2. Power of 2 comma 4 multiplied by 2. I'll finish this. So that's all. I have made all the calls, and the last call is 2 comma 0. So 2 comma 0, when n is 0, it returns 1. So this will be 1 multiplied by 2. So result is 2, and it returns here and multiplied by 2. Again it is 2 square. 2 square returns here. So this is multiplied by 2. So this becomes 2 cube, and so on. So I don't have to work out on this one. So you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times 2 is multiplied. So the result is 2 power 9. So for value of n as 9, it has made a total 10 calls. 9 to 0. Total 10 calls. So n plus 1 calls. So now you know how much time it is taking and how much memory space it is consuming. As there are 9 plus 1 calls, so it is n plus 1, and it is order of n, time is order of n, and what is the size of the stack? That is also order of n, because the number of activation records created inside the stack are dependent on the number of calls, that is n plus 1 calls. Now one more thing we should analyze here, we should observe here, total how many multiplications it is performing. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So total 9 multiplications are performed. So is it possible to compute this one with less number of multiplications? Let us check. Is it possible to do that? See, here if suppose it is 2 power 8. So 2 power 8 can be written as 2 power 2 and power 4. So this is 2 into 2 power 4. So it means if I perform one multiplication on the same value, then power will reduce by half. Power will reduce by half. And suppose it is 2 power 9, then this can be written as 2 into 2 square power 4. So because it is odd, we can't directly make it half. So first 1, 2 I have taken it out, and this I made it as 2 power 8 again. So I can make it half. So if the power is even, then I can directly half it out. So if the power is even number, then I can directly take half of the power, and if the number is odd, then I can take one multiplication extra, and then I can take half of the power. So if I multiply the number directly, then the power is getting reduced by half. So with this observation, we can write a power function faster than this one. So let us rewrite that power function. Here I will write down power function, integer. I'll give the same name, power, though it's a new version, m and n. First of all, if n is equals to 0, then return 1. Now next, check if n is even. If n is mod 2, if it is equal to 0. If n mod 2 is equals to 0 means number is even. If power is even, then I can reduce the power by dividing it by 2. So let us write that code here. So if it is even number, then return, call power function and multiply m into m. So one multiplication, that is m is multiplied by itself for one time, then this will be n by 2. That's good. So number of multiplication will reduce further. Then else means number is not even, power is not even, power is odd. If power is odd, one multiplication is extra. So I will write down return m into power of m into m, comma, n minus 1 divided by 2. If it is odd number, then one multiplication we are taking here directly, and then n minus 1 by 2. So n minus 1, it will become even number, then divided by 2. So let us take an example and trace this function and see in how many multiplications we can get the answer. So I'll take the same example, that is power of 2, 9. So we are looking at this function. This is a new version of a function which is having less number of multiplications. So let us try this. Power of 2, 9. This is 2 and this is 9. So n is 0, no, n is not 0. So n is even, no, it is not even. So it is odd, so it will enter here. So m into so and so. I will write on those things directly here. 2 into power of 2 into 2. So I'll write 2 square. See, this is m into m. So 2 square, comma, n minus 1 by 2. So that is 9 minus 1 by 2. 9 minus 1 by 2. That is 8 by 2. So it will be 4. So I will rewrite it as 4. So 2 square, that is 4, comma 4. So this is the call. Now again a call is made. This time this is 4. That is 2 square. So 2 square and this is 4. So 4 is not 0. 4 is a even number. Even number, just there is a call with multiplying m into m and n by 2. So let us take a next call, that is power of m into m. M is now 2 square. So it becomes 2 square into 2 square. And this should be by 2. So 4 by 2. 4 by 2. That's what we have to do. So you can see this line. So this I will rewrite. So 2 square into 2 square. This becomes 2 power 4. And 4 by 2. So this becomes 2. This is a new call again. Then let us continue. 2 power 4 and this is 2. 2 is not 0 and 2 is even. So it will enter into this part. So next call, that is m into m. Power of 2 power 4 into 2 power 4, comma, n by 2. So this is 2 divided by 2. So I will rewrite this one. So this becomes 2 power 8 and this becomes 2 by 2 is 1. Now this call, this is 2 power 8 and this is 1. This time n is not 0 but even n is, this time n is not 0 and n is not an even number, it is 1. So it enters into odd part. So in that, m into power of so and so. So m is how much? 2 power 8 into power of m into m, that is 2 power 8 into 2 power 8, that is 2 power 16, comma, n minus 1 by 2. 1 minus 1 by 2, that is 0. So this is the last call. Now n has become 0. So for 0 it returns 1. So this for 0 value, the return result is 1. This is 1. Now what it will become? 2 power 8 into 1. 2 power 8 into 1. So this is 2 power 8. And 2 power 8 goes here. So this becomes 2 power 8. And 2 power 8 goes here. This becomes 2 power 8. There is nothing. No multiplication is there. Just return. And 2 power 8 goes here. So this is 2 into 2 power 8. 2 into 2 power 8. So this is 2 power 9. And 2 power 9 goes here. So wherever the call was for odd number, there is one multiplication. Even number, there is no multiplication. Simply it returns the value. So finally we got the answer, that is 2 power 9. And total how many multiplications we perform? One multiplication, and here we have taken square of this. This was 2 into 2 actually. So 1, 2, then 3, 4, and 5. Here also one multiplication, 6. So just in 6 multiplication we got 2 power 9. In the previous version, for this one, it has taken total 9 multiplications for getting the answer when the power was 9. But now for power 9, this has worked faster and we got the result in just 6 multiplications. So that's all about this power function. So we have a faster version of exponent, that is power function also. The same function can also be written using iteration, that is using loop. So that's again a student exercise. So you have to do it. So we will continue looking at more example of recursions in coming videos. In this video, we will implement power function. We have seen two versions of power function. So I will show you the first one. Let us write a function called power for finding power of. Let us write a function called power, which takes parameters mn, n. It will raise m to the powers of n. If n is equals to 0, then return 1. Otherwise, return power m is as it is, but n will be reduced by value 1. And it is multiplied by m. This is what the function we have seen. So the same function I have written here. Now as usual, inside main function I will declare a variable r, and to this I will assign power of 2, 9. Then I will print the value of r. That's all. A program is ready. I will run the program. So there was a mistake here. So that's all. A function is ready and I am calling that function. Let us run the program and see the result. 2 power 9 is 512. I should get the result 512. Yes, it's perfect. I will change the values. 3 power 4 is 81. Yes, we got 81. So it's working perfect. I will write another function. We have seen two functions. Another function I have shown you with reduced number of multiplications. I will call that function as power 1, which takes m and n. Here, if value of n is 0, then return 1. Then, if the number is even, that is n mod 2 is equals to 0, means if it is even, then return call power 1 by passing m multiplied by m and n by 2. Else the number is odd, so return m multiplied by power 1 of m into m comma n minus 1 by 2. That's all. This is the function we have seen. This will take less number of multiplications to find the result. So I will just change the function name to power 1 and let us run the program and see. It should give me 81. Yes, it's perfect. Now if I pass 2 power 9, then what's the result? It's 512, it's perfect. If I say 2 power 8, here I have changed the value. Let us run. 256. Let me try one more value. 9 power 3. Yes, it is 729. So that's all. With power function we have seen both the versions. So you can try this program, you can write the program. Now in this video we will learn about Taylor series. We will learn how to write a recursive function for Taylor series. First of all, we will generate the idea how we can prepare a recursive function for this one. Let us observe Taylor series, then we will devise a method for writing a recursive function for Taylor series. So let me read it out. See, e power x, so for any given value of x, it is nothing but summation of these terms. As many terms as you take, we get more precise value. So here it is n term. So you can continue the summation up to some term, few terms, whatever you want. Here in the example, I have written up to power 4, that is total 5 terms, that is power 0 to power 4. Now, how to write a recursive function for this one? So, if you observe, there are 3 operations performed in this one. One is summation of terms, and another one is power of x. X is raised to powers every time. Then, in the denominator, there is a factorial of 1, factorial of 2 and 3 and 4, so on. So there are 3 values that are involved here. In our previous videos, we have already written recursive functions for sum of first and natural numbers, that is sum of first and natural numbers 1, 2, 3 goes on to n. And we have also written a function for finding factorial of n, that is number n, that was 1 into 2 into 3 into goes on to n. And we have written a function for finding power of x power n, that is m power n we have taken. So this is x into x into x into x goes on for n times. We have already seen this. We have already written recursive functions for this. We said that sum of n is sum of n minus 1 plus n. So we have written it like this, sum of n minus 1 plus n. And this factorial of n minus 1 then into n. So we have written it like this, factorial of n minus 1 into n. And this we wrote power up to n minus 1 times. So this was power up to n minus 1 and into x. So we have written these recursive definitions already. Now for Taylor series, actually we have to combine these 3 and write a recursive function for that one. So let us observe few things. Here if you see the first value n, so the recursive call will start from n and it will be go on reducing up to 1. And then it will start adding. So the addition of values is done at returning time. So actual addition starts from 1 onwards. So if I take the value of 4, sum of 4, then this will call sum of 3 and plus 4. This 4 will be added at returning time. Then sum of 2 plus this 3, sum of 1, then plus 2, sum of 0, then plus 1. The sum of 0 is 0. So while returning, this is 0, then this is 1, 1 is added, then this in this 1, 2 is added, and total is 3, and then here 3 is added and here 4 is added. So you can see that the addition is done at returning time. So similarly, for finding factorial also, product is done actually at returning time. So the starting point will be 1 and the last value will be multiplied will be n. And similarly in the power also. Now, for Taylor series, what we want is, we want 3 things: summation and power, as well as we need factorial. So this x is raising to some powers and also we are getting factorial. Now a function for Taylor series must perform 3 operations, but the function can return only one result. Like this is sum of three numbers plus 4. Like this is sum of two numbers plus 3. So here sum of these terms plus this term we can do. But what about the power and factorial? So power and factorial cannot be returned by a function. Function can return only one value. So when you have to involve multiple values in a recursion, then you can use static variables. So let me show you how we can frame a recursive function for finding e power x using static variables. First, I will try to devise the method, then I will write down a function for that. Let me take the example for e power x for 4 terms, means total 5 terms it will be. So highest degree is 4. Now let us devise a recursive procedure. For that, I'll take the example up to power 4, that is highest power 4. So let me write the function as x and 4. Let us start with this one. So I am first doing the tracing, then I will write down the function based on that. Now what we want, so when it is x comma 4, it should call itself by 3. So okay, it will call itself by 3. Then it should call itself by 2. Okay, then 1, then 0. Now when it is 0, it should return 0. So okay, it will return 0. So the result of this is 0. Now what we need for this term, actually for this function, we are here. So what it should do, x by 1 it should do. So okay, I will write it as 1 plus x by 1. 1 plus x by 1. This is what I want, x by 1. Now this result is returned here. So the result of this function will be 1 plus x by 1. Now for this term, for this function, what I want is x square by 2 factorial, and this should be added. So I need this x and 1 so that x is multiplied with numerator, so it becomes x squared. 2 is multiplied with denominator, so it becomes factorial. Then when I go back again here, so this result will be given to this function. So the result of this function is 1 and x squared by 2 factorial. Now for this function call, it should be x cubed by 3 factorial and plus 1. So in this function call, it should become x cubed. So for making it as x cubed, I need this x square. So in that I can multiply it by x and obtain x cubed, and then I need 2 factorial, so that I multiply it by 3, so it becomes 3 factorial. Now for handling these two values, that is numerator and denominator, I take 2 static variables. First is x power, so this is power, p I will take, and then next is denominator, that is factorial, so I'll take it as f. Now initially I will write them as 1 1. So assume that this is x power 0 and this is 0 factorial. So we have these initial values, that is for the first term. Assume this. Now let me trace this once again. So I'll remove these and I will utilize these static variables in this recursive calls. Now let us start again. For this function call x comma 4, that is I want total 5 terms, that is highest power is 4. So for this it will call itself with 3, then 2, then 1, then 0. So for 0 it should return 1. So that is this term, that is 1 it is returning. Now when it goes back here, what it should do? I need the term 1 plus x by 1 for this call, So let us multiply this p with x and factorial with 1. So this x and this one, this x and this one, this x is multiplied with p and this one is multiplied with f. So this, let us write it as p by f. So this is p by f. So this one is the result obtained by this function plus p by f. So I will write down the steps once again. This is p is assigned with p into x. This I have to do, and then f is assigned with f into 1. This I have to do. Then the result of this one is 1 plus this is p by f. So p is x and f is 1. So this is x by 1. So this term is x by 1. So these are the 2 steps every time I will be performing. So I will not write them every time. Directly I will be using this 1 by p power x, and these operations I will perform here. Now let us continue. It goes back with the result. What is the result? The result of this function is 1 plus, what is p by f? P is x and 1. So this will x by 1. Now in this call also it has to perform this. So this becomes into x, that is x square, and f becomes into 2, this is 2, so into 2, so this is 2 factorial, and plus, now in this result it is added. So what is added? P by f. So p is x square and by f is 2. Then the result of this function is returned. The result of this function is returned. So this becomes 1 plus x by 1 plus x square by 2. Now for this function call, again this p should be multiplied by x and f should be multiplied by 3. So it becomes x cube and this becomes 3 factorial. So plus x cube by 3 factorial. That is 6. Now this is the result of this function call, so this returns and this becomes 1 plus x by 1 plus x square by 2 plus x cube by 3 factorial. Now these steps, as I said, I will not be writing them, but I am performing every time. So into x, so p again into x, this becomes p x power 4, and this is into 4, so this becomes 4 factorial. So that term is added and this is x power 4 by 4 factorial. So result of this function will be 1 plus x by 1, x square by 2 factorial, x cube by 3 factorial, plus x power 4 by 4 factorial. So that's how we are getting the result of a Taylor series for highest power 4. Now let me write a function for this one, which is utilizing variables that are static p and static f and x and n. By using these static variables, we will write a function. So let me write the function here. Return type is integer, function name is e, and taking two parameters x and n. Now here I need two variables. So first of all, I declare some variables that are static int p, that is 1, and f, that is also 1. Then I need one more variable. The result of this function is added by p by f. So I have to take one more variable to store the result of a function. So I will take one more normal variable, r. If n is equal to 0, then when n is 0, it is returning 1. Return 1. Else, what are the steps? First, call itself. So first is call. So e, x is as it is, and n minus 1. The result of this function should be taken in some variable. So for that I have taken a variable r. Let it be in r. Then here in the basic step, I have shown you that p is multiplied by x and f is multiplied with the value of n. So let us do this. P assign p into x and f assign f into n. So these two things will be happening at returning time. So at returning time, the power will be growing. By the time it return back to the first call, p will be having x power 4 and f will be having 4 factorial. So those two are performed in returning time. Now what I have to do? I have to take the result of a function and plus p by f. The result of a function plus p by f. The result of a function plus p by f. Result of a function p by f. This is what I have to go on returning. So return result of a function r plus power by factorial. So this is a recursive function for Taylor series, that is e power x. For the same Taylor series, we'll look at one more approach, which is faster method and takes less number of multiplication for getting the result. So I will show you the approach, and also I will write a recursive function for that one. In this video, I will implement a function for Taylor series, that is finding e power x, that we have already seen in the previous video. So just I will write a function and just I will give you a demo of that function. Function name I will call it as e, but return type I will take it as double. While explaining on board, I have used integer most of the places, but actually the result is in decimal point, so I should take either float or double. So I am taking double here, and the parameters are x and n. See, x is the power of e and n is how many terms we want. So the more number of terms we take, we get more precision. Then inside the function, we are using static variables, which I will declare them as double, that is p assigned 1 as well as f assigned 1. Then if n is 0, return 1. We need one more variable, r, for storing the result, so I'll declare it as double, and that r assign e x comma n minus 1. And every time p is multiplied by x and f is multiplied by n, that is for denominator and it is a factorial, and return r plus p by f. So that's all, the function is ready. Then from main function I will call it. Directly I will write the result inside printf. Call function 1 comma 10. So e power 1. It should give the result e power 1, and the number of terms that we want are 10. If I want more precision, then this 10 instead of 10 I should give more larger number. Let us run and see what is the output of this function. E power 1 is 2.718282. Let us check it on a calculator. 1 e power x. Yes, 2.718281. So I got the correct result. Let us try with another value. I'll give the value 3 and run it. See, the answer is 20.079665. Let us try it here on the calculator. 3 e power x, 20.08557. And here we got 079. So it is little less than that. So if you want more accurate value, then increase the value from 10 to 15 or 20. So you can give some another number. Let us check for 4. It is 54.44. And here on the calculator, 4 e power x, 54.59. So this is little less than that. If I increase the number of terms, instead of 10, I will give 15. Let us see what result we get. Yes, 54.597, 54.598. So still our value is little less than that. So I can still increase the number of terms to get more precise value. So that's all. This function is finding e power x, that is the result of Taylor series. That's all in this video. Now let us take a different approach for evaluation of a Taylor series. And this method will be faster by taking less number of multiplications. So where actually multiplications are done. So for evaluation of factorial, 4 factorial, that is multiplications are more in number, and then x power 4, then x has to be multiplied by 4 times. So there the multiplications are. So for each term we have to perform some number of multiplications. If you analyze for 4 degree 4, that is power 4, total how many multiplications are required? Let us do the analysis. For this term there is no multiplication, and here also there is no multiplication. This term x square, so x into x, so we need 1 multiplication, and this is 1 into 2, we need one multiplication. So total 2 multiplications are there. And here x cube. So this is x cube means x into x into x. So these are 2 multiplications, and this is 1 into 2 into 3. So these are 2 multiplications. Total 4 multiplications are there. Now x power 4 means total 3 multiplications will be required in numerator, and I'm just writing multiplications, and here 3 multiplications will be required in denominator. This is 6. So it means next term it requires 8 multiplication and 10 multiplication. So this is how we are getting the multiplication. So if I take 2 common, this is 1 plus 2 plus 3 plus 4 goes on to n terms. So this is summation of n terms. So this is n into n plus 1 by 2, this one, and the result is n into n plus 1. So if you are evaluating a Taylor series for n terms, then total how many multiplications required? N into n plus 1 number of multiplications required. So this is nothing but order of degree of n square. So I can say that n square multiplications are required. Yes, roughly, means it's not exact, you don't have to take exact. N square is sufficient to understand that these are more in number or huge in size. So for evaluation of Taylor series by taking term by term, so for each term some multiplications are required and total multiplications are n square. Can we reduce the number of multiplication? So let us see how we can reduce the number of multiplications. Now I'll show how we can reduce multiplication. So here I can take the terms common. So let us start. I will take up to power 4. So I will rewrite that formula: 1 plus x by 1 plus x square by 1 into 2 plus x cube by 1 into 2 into 3 plus x power 4 by 1 into 2 into 3 into 4. Now in this I can take x as common for all and denominator is 1. So this is 1 plus, when x is taken as common, so this is x by just 1 into 2. So let us just write it 2 plus x square. X is taken as common and 1 is taken as common. So this is 2 into 3, and plus x is taken as common. So x cube by 2 into 3 into 4. So I have taken first common term. Numerator and denominator both have reduced. Now let us see if we can take more common values. 1 plus x by 1 and 1 plus, in this I can take x by 2 common. Yes, x by 2 is there. So this is x by 2, and here it is 1 plus, as x is taken, so this is just 1x and 3 plus, and here x is taken, so this is x square by 3 into 4. Then 1 plus x by 1, 1 plus x by 2, 1 plus, here I can take x by 3 common, and this will be 1 plus x by 4. So that's how by taking commons I have reduced the number of multiplications. How they are reduced? Let us see. See here there is one multiplication, and this term is multiplied here. So this is one multiplication and this is another multiplication. So 1, 2, 3. And if you consider this is multiplied by 1, so let us say 4. So only 4 multiplications are required. So if you want up to 4th term, that is degree 4, power 4, then only 4 multiplications are required. So the number of multiplications has reduced to order of n. It's not square. Earlier that was a square. So now it has reduced to order of n. So yes, by taking commons, we can reduce the number of multiplication from quadratic, that is square, to linear. We have reduced the time. Earlier it was n square. This is quadratic. So the time was quadratic. Now the time is linear. So this is faster. So one observation is by taking commons, we can reduce the number of multiplications. Now, how to write a recursive function for this approach? Now, let us write a recursive function for this. Now, let us observe this form of Taylor series and let us see how we can devise a recursive function for this one. So, first let us observe. If I call this recursively by passing x and 4, then it may be at 4, then it will call itself for 3, then 2, then 1. But if you observe, this result has to be multiplied with this one, plus 1 is added, and the result is multiplied with x by 2 and plus 1 is added, and the result is multiplied. So actually multiplication is done in this form, or actually multiplication is done in this order. First x by 4, then with x by 3, then x by 4. So, and returning time, there is nothing. If you are multiplying and adding 1, multiplying and adding 1, returning time, there is nothing. So usually the recursive functions that we have written, they were performing the operations mostly at returning time. But here at calling time itself, I should find out this term and multiply it with x by 3 and add 1. So I get this term. Then this I should multiply by x by 2 and add 1. Then I get this term. Then this result should be multiplied by x by 1 and add 1. So I get the complete result. So it means when I did for x by 4, so that I should multiply it by 1 and add 1. So actually the processing is done at calling time only. So when the first call is 4, before calling the next call, that is 4 minus 1, that is n minus 1, it should perform the multiplication. So this is happening at calling time. So this can be easily written using loop. So first let me write down how it can be done using loop, then I will show recursion. So let us write a function for loop. Integer e, integer x and integer n. Now in this I have to start from this term, right? This term. So I will take some variable for holding the result. So let us take one variable integer s, that is initially 1. Now what I have to do in each step, x by 4 multiplied by with the result s and added 1, and this becomes a result, and this is multiplied by x by 3 plus 1 and this become a result. So result I am taking it in s. Every time s should be multiplied by x by n, whatever the value of n is. Right now it is 4 if you start from here, then plus 1 is added and this result should be taken in s only. So this is in s. So this step I have to keep on repeating. So for how many times? For n is greater than 0 and n minus minus. That's all. So n is right now suppose 4, then it will become 3, then 2, then 1. So it will get multiplied and finally we get the result. So we can return s. So this is the step perform every time. So if n is 4, so it is performed for 4 times and the result is returned. So this is easily possible using loop. And here I have not taken any extra variable I, because whatever the value of n is, from there I am reducing. So there is no initialization part, just semicolon and the condition semicolon and n minus minus. So if n is 4, then it will become 3, then 2, then 1 and then 0. When it is 0, it will not repeat, but it will return this s. So s is having the result. Now same thing I can write using recursion, but in recursion I have to perform multiplication at a calling time. So at a calling time if I have to do, then I can take the help of static variable now. So let us write it with the help of static variable. So it will be on the same fashion. Recursive function, this is a recursive version, x and integer n. I need one static variable for storing the sum, and whose value is 1 initially, this one. Now if n is 0, means when it has reached 0, do nothing but return s. So here also I will write down s. Else, what I have to do? Else, perform this operation. So the same operation I'll perform, s assign 1 plus x by n multiplied by s. The next is, as it is repeating, so here call itself again by e, x and reduce value of n, that is n minus 1. And here I should write down a statement that is return. That's all. So already we have discussed in our previous lectures that loops will have just ascending, there is no descending, but recursion will have ascending and descending. But this procedure can be performed only in ascending. So I have taken a static variable and I am storing the result in that one at calling time itself. So this is a iterative version and recursive version of a function for evaluation of Taylor series with order of n number of multiplication, that is a reduced number of multiplications. So that's all with the Taylor series. Now similarly there are more series like sine series and cos series. That is your student exercise. So you have to write on the functions. So you try to write on those functions. So here in this video we'll look at a recursive function for finding e power x, that is for Taylor series. We have already seen the procedure using Horner's rule in the previous video. That same function I will implement here. Already I have a body of a function. I will implement a function. I'll take a static double value s. While explanation I have taken it as integer, but the result is double type or decimal type. If n is equal to 0, return s. Otherwise, s is evaluated as 1 plus x divided by n into s. See, x and n both are of type integer, so I'll get integer division here. So I should typecast it as double, or else I can multiply x numerator with s beforehand, so that this result becomes double, and then divided by integer also gives double. So writing statement will give a perfect result. Otherwise I have to typecast x by n. Now the next statement is return the function called x comma n minus 1. That's all. Inside the main function, I will directly print the result obtained by that function. So printf percentile lf, then slash n, call the function e1 comma 10. Let us run the program. We already know the result. Let us see whether we get same result or not. Yes, 2.718282. If I give the value as a 2, yes, it is 7.38871. Let us check it on a calculator. 2 e power x is 7.389 and we got a 388. So it is less, little less. If we want more precise value, then we can increase the number of terms. So that's all the implementation of Taylor series using Horner's rule. Yeah, in this video, we'll look at implementation of function for Taylor series using iterative method, that is using loop. So already I have the body of a function. I will implement the body. I'll declare a variable s that will be initially 1. Then for iteration, I will take one variable I. We need numerator and denominator, so I will take double numerator, that is initialized with 1, and double denominator initialized with 1. Next, for loop will start I from 1 onwards and going up to n, I plus plus every time. Now inside for loop, numerator I should multiply every time by x and denominator should be multiplied by I every time. So I is 1, then I is 2, so we'll get the factorial. Then s should be added with numerator by denominator. At the end outside the loop, return s. So this is a iterative version. Let us print the result obtained by that function, percentile lf, new line, then call function by passing 1 comma 10. So we already know the result, we should get the same result. 2.718282. Yes, perfect. So this is the implementation of Taylor series for finding the value of e power x for 10 terms for a given number of terms. So that's all. Now the topic is Fibonacci series. So here we will learn what is Fibonacci series, and then we will devise a recursive definition and we will write a recursive function for that one, and finally we will analyze that function. So let us start. See, this is the Fibonacci series. The 0th term is 0, next term is 1, then 2, then 3, then 5, and so on. So how we are obtaining these terms? each term is obtained by adding previous two terms. So that is 5 plus 8 is 13, and this term is obtained by adding these two terms. So initially, what are the terms? These are the starting terms. Means if it is 0th term, then it is 0. If it is a term 1, then it is 1. Rest every other term is obtained by adding previous two terms. So initially you must have two terms, then only you can define like this, that every term is obtained by adding previous two terms. Alright, so this can be defined mathematically. Fib of n can be defined as fib of n minus 2 plus fib of n minus 1 when n is greater than 1. If n is 0 or n is 1, then if for 0 it is 0, for 1 it is 1. So if n value is 1, the answer is directly 1. For n is 0, the values are directly 0. For n is equals to 1, answer is directly 1. Otherwise, add previous two terms. So let me put it in a table. Now this is term number n and this is fib of n. Suppose I want to know 5th term, answer is 5. If I want to know 7th term, answer is 13. So first let me write a recursive function for Fibonacci series. Based on this recurrence relation, or based on this recursive definition, I will write a function integer fib of integer n. So here it says that if it is 0, return 0, if it is 1, return 1. So it means if n is less than or equal to 1, return n itself. Means if n is 1, return 1, if n is 0, return 0. Otherwise, return fib of n minus 2 plus fib of n minus 1. This is a recursive definition. That's all. If you want to find out any term like 7th term or 10th term or any term, you call fib of 10, you get the 10th term of Fibonacci series. Call fib of 7, you get 7th term. We'll come back to that function afterwards. So first of all, let us write a iterative version, that is a function using loop. So let me write a Fibonacci function using loop. Integer fib, I'll give the name fib once again, same name I'm using here. Then if the number is less than or equal to 1, then return the number itself. So here, if n is less than or equal to 1, then return n itself. Right? Otherwise, I need two terms to add them one by one. So integer term 0 is 0 and term 1 is 1. And also I have to add the values. So for addition, I will take sum s. So I have three variables. Now using these three variables, I will write down a loop for finding out nth term. See, suppose I have to find 7 terms, then already term 0 is available, term 1 is also available. Then I have to obtain this term 1, 2, 3, 4, 5, 6. So actually I should generate only 6 terms. So I should perform additions only 6 times. Already I have these two terms, right? So 2, 3, 4, 5, 6, 7. That's all. So I should start from second term onwards and stop at 7th term. So whichever term I want, I should stop that. So I should start from 2 onwards. So let me run a loop for I assign 2. So I need one more variable I, and I is less than or equal to n and I plus plus. So this is for repeating the procedure for n minus 1 times, or I am starting from 2 to n. Now every time what I have to do, s should be assigned with t0 plus t1. So this term should be obtained by adding these two, that is t0 and t1. Then after getting the sum, now this should become t0 and this should become t1. So for getting the next term, so I should change this value t0 and this I should make it as t1. So T0 should be made as T1 and T1 should be made as S, and repeat this procedure. So finally a result will be in S. So this is a iterative version. So iterative version, what is the time taken by this algorithm or this procedure? This procedure takes, let us take it, this statement will execute for one time and one time. This loop is written as 1 plus n plus 1, but starting from 2 onwards, so let us say it is only n, and the things inside will be for n minus 1 times, and this is 1. So total is 1, 2, 3, 4, 4n, and minus 1, 1, so this plus 1 gets cancelled, so it is 4n, so the time is 4n, so it is order of n. Basically we wanted to know the degree, so it is order of n. So we don't want exact formula, we want the degree. You can see that there is one for loop, and for loop will repeat for n times, so the time is order of n. It's obvious from the function. So this algorithm takes order of n time. So already we have written iterative version. Now let us go back to recursive version and analyze that one and see how much time it takes, and if any improvement required, we will do some improvements in that. So I'll remove this one and then we will analyze that function. Now let us trace this recursive function for fib of 5. If we pass 5, what happens? 5 is not less than 1, so it will make 2 calls. So we know the function is very simple, so I will just go on tracing this one. So here it will call fib of 3, and there it will call fib of 4 afterwards, not now. First this call will be made, as this is 3, so it will make a call for fib of 1 and fib of 2 afterwards, not now. Fib of 1, this is the end when n is less than or equal to 1. So yes, n is 1 now. So this will not call further and the result is 1. Then here it has to call fib of 2. So I'm just writing f here for fib. Then fib of 2 further calls fib of 0 and fib of 1. Fib of 0 gives the result 0 and this gives the result 1, and they are added, result is returned, and this is added, result is returned. And here it will call fib of 4. So for fib of 4, this is fib of 2 and this is fib of 3. Fib of 2, fib of 0 and fib of 1. So these results are obtained 0 and 1 and they are added, result is returned. And on this side, fib of 3, again this is fib of 1 and fib of 2. Then fib of 2, this is fib of 0 and this is fib of 1. So here the call is, so here the result is 0 and this is 0 and this is 1, and added, return, added, and final addition is done. So this is how a tree looks like, a recursion tree looks like for fib of 5. If you look at the functions in the order in which they are called, this is the first function call and the second call and the third call, then fourth call, fifth call, then sixth call, then seventh, 8, 9, 10, then this is 11th call, 12, 13 call, 14 call, 15. So for fib of 5, number of calls are 15. Then fib of 4, how many calls are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 calls are there. Then fib of 3, how many calls are there? 1, 2, 3, 4, 5. 5 calls are there. So now if we try to observe any pattern, there is no pattern here. This is 5, so this is 15. 5, 3 is 15. Then 4, 3, it should be 12. Then this is 4 into 4 or 2 into 4 plus 1. So we cannot figure out what pattern it is following. So if you want to know the time taken by this one, then assume that this fib of n minus 2 is also fib of n minus 1. So this is calling itself for 2 times n minus 1, n minus 1, n minus 1. So when a function is calling 2 times by a reduced value of 1, n minus 1, then the time is order of 2 power n. So the time taken by this function is 2 power n, approximately 2 power n. So if you observe, the previous function iterative version was order of n and recursive version is 2 power n. too much time consuming. Now, is there any method to make it faster than 2 power n? Let us observe. Now, this analysis is important. If you see the tracing tree, that is recursion tree, the value of f3, function f3 is called here, and again it is called here. F2 is called here first time, then again F2 is called, then again F2 is called. So similarly, F0 and F1, they are also called multiple times. So a recursive function is calling itself multiple times for the same values. So such a recursive function is called as excessive recursion. So yes, this Fibonacci function is a excessive recursion because it will call itself multiple times for the same parameters. This is the problem in this one. So is there any way to avoid the excessive calls and just make a call only once and utilize it in further calls? So yes, what is the method? Let us devise a method. If you want a function to retain these values so that they can be utilized here, then for retaining the values you have to take the help of static variable, or you can also take global variables. Let us take one array, maybe a static array or global array, whatever you want, you can take it. Index 0, 1, 2, 3, 4, 5, 6, as much size as you want you can take it. So just I have taken some size, we want up to 5. Now how to write now how to modify this algorithm to make it faster? So I'll remove few things from board and show you. This global array or static array, let us initialize it with -1. -1 means we don't know the value, -1. Now, let us trace it once again by taking the help of this global or static array. First, I will show you the tracing, what modifications we can do, then we will modify our function. Let us see. Call fib of 5. Do we really need to call it? Check f of 5. -1. We don't know the answer for this. Okay, call this one. So, when it is called, it will make 2 calls. So, the first call. Fib of 3. Do we really need to make fib of 3? Yes, we have to because we don't know the answer. Then this will make fib of 1. Do we need to make a call for fib of 1? Yes, because it is -1. Okay, make the call. So once you make the call, the result is 1. So once you got the result, because this is a small function, see if n is less than or equal to 1, return 1. So return 0 or 1, whatever it is. So this is 1. So we got the answer. So change this to 1. Now we know the answer for fib of 1. Yes. Then go back. Do we have to make a call to fib of 2? Yes, we don't know the answer. Then do we have to make a call to fib of 0? Yes, we don't know the answer. Call this function. So this result will be 0 as per this one. When it is less than or equal to 1, return the same value. So 0 returns 0. So modify this also. Now we know the answer for those two. Then make a call for this one. Do we need to make a call for this? Check. No, we know the answer. Don't call this. It's not called. Yes. So avoid the call because already we have got the answer here. So this call is skipped. Then I have to get the answer for this one. This was 0 and this was 1. So this is 0 plus 1 is 1. So this answer is 1. So modify this one. We know the answer for this. Then we got this answer 1 and this answer 1 plus 1. So this is 2. So we got the answer that is 2. Then let us go on that side. Fib of 4. Do we know fib of 4? Check it. No, we don't know. So we have to call this one. So if you call this, then there are 2 calls inside. Fib of 2. Do we know it? Yeah, we know it. Don't call this one. So don't call this also. So further calls will also be avoided. Then the result we know how much it is. It is 1. Fib of 2 is 1. Then fib of 3. Shall we call it? Check it. No, we know the answer. So don't call this one. So then following calls will also be avoided. And the answer for this one is how much? 2. Then perform addition. 1 plus 2. This is 3. Now we know the answer for this side also, that side also, plus. So this becomes 2 plus 3, that is 5. So this I did not update this. So now this is 5. We know the answers for all. So these calls are avoided. So if you remove those calls and check 1, 2, 3, 4, 5, 6. So it is making just 6 function calls. For 5, 6 calls. Reason 5, 4, 3, 2, 1 and 0 is also included. So for n, how many calls? N plus 1. That is n to 0. So the time taken by this method will be order of n. So time is reduced. So just now you saw that function, if we analyze, it will take order of 2 power n, that is exponential. I did not analyze it thoroughly, just I have told you that it takes 2 power n time approximately. That is upper bound, 2 power n is an upper bound. But now by storing the result of the function in an array, we have reduced the excessive calls and the time is less than 2 power n and it has reduced down to just order of n. So a big change in the time complexity of Fibonacci function. So this reduction in time is because of storing the values in an array, holding the results so that avoid excessive call. So this approach is called as memoization. Storing the results of the function call so that they can be utilized again when we need the same call, or avoiding excessive calls. This approach is called as memoization, means storing the results. So this is applicable here in Fibonacci series. So I have given introduction of memoization. So this is an example, suitable example for memoization. Now based on this memoization, I have to modify that function. So I will remove the function and write a better function that is using memoization. Let us write a function. Suppose there is some global array f which is initialized by some function, let us say main function. All minus 1 are filled in main function. Now Fibonacci function. Fibonacci function takes parameter n, and if n is less than or equal to 1, then in f of n store the value n and also return n. So if you observe, the previous function was having just return n, but now this function is also storing the result in global array for memoization. It is storing in f. Then else part. Else, earlier blindly we were making two functions call, that is fib of n minus 2 and n minus 1, but now we check and then make a call. If value is not known, then we'll make a call. So if f of n minus 2 is minus 1, means if you don't know the value, then f of n minus 2, you get the result of fib of n minus 2. So here we will make a call. Similarly, if we don't know the value of fib of n minus 1 and it is minus 1, that we don't know, then make a call for fib of n minus 1 and store the result in f of n minus 1. Now we have two values, then simply return addition of these two values, that is fib of n minus 2 plus fib of n minus 1. So this version is with memoization. Assume that global array is initialized with minus 1 somewhere inside main function before the function is utilized. So that's all about Fibonacci. We have learned that it can be written using iteration, then using recursion, and the time is order of 2 power n. Then we have reduced the time by using memoization. So that's all. In this video, we'll look at a function for Fibonacci series. First of all, I will show you a iterative function that I have explained you in the previous video. I will write a function. I will call the function name as fib. It takes parameter n, that is the term number that we want to find out in the series. So inside the function, first of all, I will write a return 0, because if you see this error message, function is having int return type, but it is not returning anything. So that's what the error is. Control reaches end of non-void function. So to avoid this error, for time being, I will write down return 0. Then later we'll see what we have to return. So this error is gone. Now I will write on the function. I have taken some variables like t0 initialized with 0, and t1 initialized with 1 and s for finding sum, and also we need variable I for loop. Then the very first thing inside a function is if n is less than or equal to 1, then return same number n. Otherwise we'll find out the term using for loop. So for loop will start I from 2 onwards and I reaches less than or equal to n, then I plus plus. So it will start from 2 and reaches up to the term number, nth term. So every time we have to find out sum, that is by adding t0 and t1. Then t0 should get the value of t1 and t1 should get the value of sum, that is new value that we have obtained. By repeating this loop for n times, we get the result in s. So then last statement should be return s. Earlier I wrote it as 0 to avoid error, return s. Here I am getting a warning that s may be uninitialized when used here. If it doesn't enter into for loop, s will not be modified and s is having some garbage value. So let us initialize s with 0, so this warning will be gone. We'll not get any wrong answers due to this, but to avoid this warning, I have just initialized s to 0. Now inside main function, I will directly print the result obtained by that function, %d and new line. Then I will call the function fib by passing 10. That's all. So now the whole program is ready. I will run the program. Here 10th term is 55. Let us see 5th term. Answer is 5 for 5th term. Yes, the 5th term is 5. Then 6th term is 8. Let us try that also. Yes, I got the result 8. So it's working perfect. Now I will write a recursive function for finding Fibonacci term. Let me call the function name as rfib for recursive. Then parameter is n, that is the term number. As we have already seen the code, if n is less than or equal to 1, then return n itself. Otherwise return rfib of n minus 2 plus rfib of n minus 1. That's all. The function is so simple because it's recursive. It has finished in just 2 lines. Instead of calling fib, I will call rfib here inside the main function. Now let us run program and see what the output is. For this it should get 8. Yes, rfib is also giving 8. Now to reduce this number of calls, we have seen memoization. So I will write on a function using memoization. So already I have one function, that is a iterative function called fib, then recursive function for Fibonacci. Then next I will write a memoization function for Fibonacci. For memoization function, we need one global array f. So I will take the array size as a 10, limited size. If you want larger, you can take it. And inside the main function, I will first initialize this array. Using for loop, I will initialize for I assigned 0, I is less than 10, I plus plus. If you remember, the array should be initialized with -1. So all these locations I will fill them with -1 because 0 is also a Fibonacci term. So we should have the term, so we should have a number, not a Fibonacci term. So -1 is not a Fibonacci term. So I have initialized this array with -1. Now here I will write down a memoization function. That is a function for finding Fibonacci term using memoization. Integer is the return type, so I will call the function name as mfib for memoization. Then it's taking term number n as parameter. First thing is, if n is less than or equal to 1, then in f of n, assign n itself. and also return n. So these are two statements inside a if condition. So I will write them in flower bracket. So this is the body of if. Then else means if the number is greater than 1, then check if f of n minus 2 is equals to minus 1. If it is equal to minus 1, then call mfib of n minus 2. Call this function. And whatever the result we obtained, take it in f of n minus 2. So I am writing in a single line. Okay, I will take it in the next line. Then next one, again for n minus 1 also I have to check it. If f of n minus 1 is equal to minus 1, then call the function for n minus 1 and take its result in f of n minus 1. So call mfib of n minus 1. Once we have got this result, whether the function is called or not called, we get the results here, then return f of n minus 2 plus f of n minus 1, because the results are kept in a global array f. So that's all. This is a function using memoization. So f is a global array that will help this function to store the results of the function to avoid excessive calls. Now here inside main function, instead of calling rfib, I will call mfib for 5 and I should get the result as 5. I have deleted the breakpoint. Now let us run the program. Yes, the answer is 5. If I call it for 6, then let us see. 8. It's working. Now I will put a breakpoint and debug the function. So you have to count how many function calls it is making. For value 5, it should make 6 calls. I have made the value as 5, so it should make total 6 calls. Run the program. So it has came on this printf function. So you have to watch this watch window and debug navigation to count the number of calls it is making. Let us start. First call, value of n is 5. Second call, value of n is 3. So here you can see the value of n is 3, and here at this place you can see there are 2 calls. So in the previous call, it is in this statement. See, it is in this statement. So 2 calls so far. Then for 3, it has entered inside else block. Then again it is going to call itself for 1, that is 3 minus 2. So this is the third call. For 1, this conditional statement will be true and it will come out of the function after executing this if block. So we are on the third call. Third call has finished. Back on the second call. Now it is entering into second if part of this one. So it will make a call with n minus 1, that is 3 is, that is n is a 3. So 3 minus 1, 2. So for 2, it is a fourth call. For 2, it will enter into else part. Then first if, fifth call. Then second if. It has skipped because already the value of 1 is found. So total 5 calls so far. Then back on 3. So it is making a second part. So for 3, this it has finished. Now it is going to call this one. So already fib of 2 is known, so it doesn't make a call. Then back on 5. Now second part of 5. Now this is the sixth call for 4. And for 4, already fib of 2 was known, that is 4 minus 2. So that's why it didn't call this one. Then next, again, this for 3 also, that is 4 minus 1 is a 3. So for this also already value is known. It did not call this one. So total 6 calls so far. Now from 4 it will come out See, it has not expanded the function call with 4 because already the values were found. Now back on 5th, that is value 5. So it is the first call and it will terminate. So total calls are 6. Only 6 calls it has made and got the result. And if I expand this Fibonacci array, you can see that the values are filled in this one 0, 1, 1, 2, 3. Okay. For 4 and 5, the values are not there because one thing I have missed here, that is inside this, before returning the result, I should fill up the value, that is fib of n should be filled with fib of n minus 2 plus fib of n minus 1. Now let us run the program once again and see how the value of global array f are changing. You can see that the global array is all filled with -1. If I continue execution, see, first f of 1 is found. Then f of 0 is found. Then f of 2 is 1 now. F of 3 is 2. F of 4 is 3. Then f of 5 is 5. That's all. So this is how the values are being stored in global array f. So that's all in this video. We have seen 3 different versions of Fibonacci function. One is iterative version and recursive function, and the third one was recursive function with memoization to avoid excessive calls. Now the topic is combination formula. This is also called as selection formula. If the set of objects are given to us, then in how many ways we can select the subset of those objects. This formula is used for finding the number of ways we can select the subset. For example, if alphabets are given to us, A, B, C, D, E, total 7 objects are given, and I want to select only 3. In how many ways I can select any 3 of them? Like I can select A, B, C, or A, B, D, A, C, B. This is wrong. This is the same selection. Interchanging of position will not give a new selection. It's called as permutation. Interchanging position is called as permutation. So there is another formula, known formula called NPR also, but this is NCR, that is combination, that is selection. So this is a known formula. Now, how we can write a procedure or a function for evaluation of NCR? Now, one important thing about this formula is, if the value of n, I am taking it as 5, then C, then R. R can take the values from 0 to 5. So it means I can find the values like 5C0, 5C1, 5C2, so on up to 5C5. So the value of R can start from 0 and the last number is same as n. So I cannot have R greater than 5, that is n itself, or less than 0. Now next thing, how to write a function for this. So I can write on a simple function for evaluation of this formula. I'll write a function here. Return type of a function is int, and let us call the function name as C, and it needs 2 parameters, that are n and r, integer n and integer r. Now for evaluation of this formula, I should know factorial of n, r and n minus r. So these factorials I can find out by calling function fact. That is, already we have written a function for finding the factorial. We have written iterative version also, recursive version also. So we can use any of those versions and we can find out the factorial of these. So for finding the factorials, I'll take some temporary variables t1, t2 and t3. T1 is factorial of n and T2 is factorial of r, T3 is factorial of n minus r. So I got all three factorials. Now I have the result, just I can return T1 divided by T2 into T3. These must be in the brackets because both are in denominator. That's all. It's a simple function for finding NCR value for any given n and r. How much time it is taking? Factorial function we have already analyzed, and it is taking order of n time, and this is also order of n, and this is n, and this is a simple statement, so it's constant time, so we can ignore that. So it is a 3n, so 3n means it is order of n, means degree of a polynomial is n. So the time taken by this function is n. It's a simple function. That's all. We can write a simple function for finding a combination value of given n and r. Now next, can we write a recursive function for this one? So for getting the idea of a recursive function, first of all we'll look at Pascal's triangle. So let us see Pascal's triangle. Pascal triangle shows that the values of NCR can be obtained by performing addition recursively. How? Let us see this. First of all, on the top the value is 1. Then on this side extremes are taken as 1. Then this extreme is 1, then these two are added to get 2, and this is 1. Then this extreme value is 1, and this is 1 plus 2, this is 3, 2 plus 1, this is 3, and this one is 1. This side it's 1, and 1 plus 3, this is 4. These two are added to get 6, these two are added to get 4, and this extreme value is 1. So what these values are, let us see. This topmost value is 0C0, and this is 1C0 and 1C1. See, the value of n is 1, so r can be from 0 to 1. Now this row is for 2, so 2C0, 2C1, 2C2. Then this row is for 3, 3C0, 3C1, 3C2, 3C3. And the last row is 4C0, 4C1, 4C2, 4C3, 4C4. So if you want to find out the combination values for n as 4 for various values of r, you can take it from this row of Pascal's triangle. So from Pascal's triangle we can find out the values of NCR, or else we can use this formula also. So already we have seen a function using the formula, but from the Pascal's triangle can we write down a function for finding NCR value? Let us see. Let us observe Pascal's triangle. See, any value, like example 4C2 is obtained by adding 3C1 and 3C2. And how that 3C1 is obtained? By adding 2C0 and 2C1. And how that 2C0 is obtained is a direct answer. 2C1 is obtained by adding 1C0 and 1C1. So it is recursive. It's recursive. If I call this value as NCR, this value is obtained by adding these two. If n is 4 and r is 2, then what is this? 3, 1. So this is n minus 1. See, r is 2, so it is 1 here. So this is r minus 1. And other value is this one. So n, so this is n minus 1. See, r is as it is. So any NCR value can be obtained by adding n minus 1 CR minus 1 with n minus 1 CR. So based on that, I can define a recursive function here. Let the function name be C, and it takes n and r. Then here for a recursion I should define a small problem. Means when n is 0 or r is 0, what I should do. So for this you can see here, when r is 0, return 1. When n is equal to r, return 1. So extreme points, those are 1 always. When r is equal to 0 or n is equal to r, return 1. So for small values, these are the small values, 1 are the small values, and when it is 1, if r is 0 or n is equals to r. Otherwise, we will add these two terms and get the result. So else return c of n minus 1 comma r minus 1 plus c of n minus 1 comma r. That's all. So this is a recursive function for finding NCR value, that is combination formula. And this recursive function follows actually Pascal's triangle. So it means if I am trying to find 4C2, it will call 3C1 and 3C2. So for 3C1 it will call 2C0, 2C1. For 2C1 it will call 1C0 and 1C1. And 1C0, 1C1 are directly 1. For 3C0 it will call this one and this one again. So it will make the calls from bottom towards top, that is bottom up calls are made compared to this Pascal's triangle. And whenever it reaches 1, it terminates, that is the last point, because when n is equal to r or r is equals to 0, we are returning 1. So that's all about combination formula. In this video, we will see a demo for combination, that is NCR formula. First of all, I will show a simple function for finding NCR value which uses factorial. So first of all, I will write on a function for finding factorial, which we have already seen it. So fact function, if n is 0, then return 1, otherwise return factorial of n minus 1 into n. This is a factorial function. Now I will write a function for NCR, which takes two parameters, that is n and r. So inside this function we have to find out numerator and denominator. First of all, I will write return 0 here. So later on, to avoid this error, later on I will modify it. Inside the function we need numerator and denominator. So numerator comma denominator, I will take two variables. Then the numerator is assigned with factorial of n. Then denominator is assigned with factorial of r multiplied by factorial of n minus r. Then we have the numerator as well as denominator, return numerator divided by denominator. All these are integer values, so division is also integer. The result of NCR is integer type only. So we don't have to worry about any floating points. So let us look at this function once again, that is numerator is factorial of n and denominator is factorial of r into factorial of n minus r. Now inside main function, I will print the result of that function directly, printf %d and new line. Call the function NCR by passing 5, 1. 5, 1 is 5. Let us run and see the result. Yes, it is 5. 5, 2 is 10. Yes, we got 10. 5, 3 is also 10. I have modified that. So it's also 10. So it's working perfectly. 4, 2 is 6. Yes, 4, 2 is 6. So this was a simple function just using factorials, and we have few statements here to get the result. Factorial is recursive, but this NCR is not recursive. Now let us write a recursive function for finding value of NCR. So here I write the function. Let us call it as all capitals NCR. It's recursive. I should write down something written here to avoid this error. Next, if n is equals to r or r is equals to 0, then return 1. Otherwise, return NCR of n minus 1 comma r minus 1 plus NCR of n minus 1 comma r. That's all. Here inside the main function, I will make function call for this recursive one, capital NCR. Let us find the value of 4 comma 2. 4 comma 2 is 6. Yes, it's perfect. Here I will modify the values. Instead of 4, I will say 5 comma 2. It should be 10. Yes, it is 10. 5 comma 3. It should be 10. Yes, it is 10. So that's all. In this video, we have seen a simple function using factorial and also a complete recursive function for finding NCR values. The problem is Tower of Hanai. First of all, we'll learn what the problem is. See here, there are 3 towers given. These are the towers, 3 towers given. And in one of the tower, there are some number of discs kept. 1, 2, 3, 4, 5. So these discs are kept on this tower A. Now the problem is, we have to transfer all these discs from tower A to tower C. So we can just take out all these and keep them there. No, you have to take out one disk at a time. Move one disk at a time. Okay, we will transfer all these disks one by one in B. So first will come, the topmost will come here, then above that, then above that, then above that, then from here we will transfer there. No, you cannot transfer like this. You have to transfer such that no larger disk should be kept over a smaller disk. So you cannot have a small disk kept here and a larger disk kept over it. This is not allowed. So 2 conditions are there. You have to move one disk at a time. Second thing, the larger disk should not be kept over a smaller disk. So by following these 2 conditions, you have to move all this n disk from tower A to tower C. For moving all these disks from tower A to tower C, we may require one more extra tower, so that tower B is given as a auxiliary tower. So we have to move disk from tower A to tower C, that is from and to, and this is for utilization, for helping. So this is using this tower, we are using the tower, that is auxiliary tower. So from is the source and to is the destination, and other one is using. Let us call it as using. So or else you can call the tower names as A, B, C. Now the problem is not so easy. It is believed to be unsolvable problem. There is some story behind this problem. It is believed that somewhere in the world there is a temple, and near the temple these 3 towers are there, and there is a tower with 16 golden discs, and few priests are trying to move this disc from tower A to tower C, and they are doing it from centuries, and if they are successful, then world will end. So that will be a doomsday. So there is a story behind this one. So it is believed that these towers and temple is in China or in India. So this was believed as unsolvable problem. But this problem can be solved using recursion. Let us see how recursion helps in solving this problem. So we want what should be the moves such that the disk can be transferred from A to C with the help of B. So we'll take some number of disks and we will try to devise a recursive function. Now we are ready to devise a recursive algorithm for this one. I have taken 3 problems here. One problem with a single disk and second problem with a 2 disk and 3 disks. Let us solve these problems one by one. So the first problem, there is a single disk. So simply move this disk from A to C. So the problem is Tower of Hanai problem, where only one disk is given and we have 3 towers A, B, C, and there is only one disk. Then what we are supposed to do? Move disk from A to C, that is source to destination, from to 2, and with the help of tower B, though we are not using this B here because there is only one disk, we don't need B, but I am writing it. That will help me write down other procedures. Now when there are two disks, tower of Hanai, two disks are given and three towers are there, A, B, C, then what I am supposed to do? See the topmost disk, I cannot move it to C, move it to B. So this topmost disk can be moved to B. So this is a small disk, come here. That is not the destination. That is the middle tower, intermediate auxiliary tower. So that is not the destination. So moving there is temporary or moving there is recursively. So that first step is tower of Hanai, one disk from, see, this was the source and this was the destination, this was the middle auxiliary tower. Now we have moved it from this source to this destination. We have moved from A to B. So for this single disk, topmost disk, C became an intermediate tower, or this auxiliary tower. Actually, it's a destination, but we are not moving there. So we are moving here. So this becomes source and this becomes destination, and that becomes a using tower or auxiliary tower. So C, I will write it in between. Then first step is over. Now second step, move this larger disk from here to C. One disk from A to C, direct A. So that step is same as this one. So move disk from A to C using B. So though we have not used, but we are saying that we are using B. So the other tower, auxiliary tower, we are mentioning it. So this is move from A to C. That is same as this step, first step. We have already seen how to move one disk. That same step is useful here. Now what is remaining? From tower B, we have to move a disk to tower C, and this becomes an auxiliary tower. So that step is recursive step. So let us call it as recursive step. Tower of Hanai, one disk, and the source is B, destination is C, and auxiliary tower is A. So these are the three steps I got. So here I am saying move disk, right? Then what about this? This should be performed as per the first step, and this also should be performed as per that first step. So this is recursive. So this definition I have written recursively. Now if there are three disks, how to move them? Let us see. Tower of Hanai, three disk, source tower, intermediate tower, destination tower. Now we have three disks. How to move three disks? If I number them 1, 2, 3 from top, then how to move them? Now for those steps, we will use a trick here and define recursively. Observe this. I'll say that move these two disks to tower B. Move these two disks to tower B. Two disks we cannot move at a time. No, we are not moving two disks at a time. Those two disks are moved by following this method. We already know how to move two disks. We saw how to move two disks from A to C. The final disk was kept here, right? So A to C, how to move we saw. Now instead of A to C, you have to move them from A to B, right? So that is not in one step. That is in three steps. So moving two disks from tower A to tower B takes three steps, which will utilize a tower C or B something. Somehow they will be moved. So how to move, if you want to see that, follow these steps. So to make this problem simple, we are saying that move two disks. So moving two disks is not just one step, it is recursive. So how to move two disks? Already step is given. Then again, how to move one disk? Already step is given here. So let us write down that first step. First step is tower of Hanai, 3 minus 1, 2 disk. From where to where? A to B. A to B. And C is the intermediate tower. Okay, when two disks are moved there, Now third largest disk is remaining. Move this disk to tower C. Third disk. So second step is move disk from A to C using B. So move that one. Though we are not using or we are using it or not, there's a different thing. Using means the intermediate tower. Now, what is remaining? You have to move two disks from B to C. Two disks you cannot move at a time. But how to move those two disks in multiple steps already shown here. So follow those steps. Now source is not A, source is B and destination is C. So A is a auxiliary tower. So this involves multiple steps, but we write it as a single step here. So the third step is tower of Honai, two disk from B to C using A. That's all. So these three steps. So we can see that when we have three disks, we can perform it like this. So now from this three disk formula, now from this three disk procedure, we can generate the idea for n number of disks. So suppose this is n, then what it should be? N minus 1. Then what this should be? N minus 1. That's it. Because this is recursive, recursion will call itself again. So there are more steps below that call. So don't imagine it's a single step. But we are able to define it recursively. So for defining it recursively, I made a simple problem, the next little bigger problem, then little bigger problem. Now this is suitable for all n number of disks, not just 3 disks. It is suitable for any number of disks. So I have converted that into n. Now I will write down this as a recursive function and I will take an example and trace this function and show you really these steps will solve the problem or not. Now here is a recursive function for solving problem Tower of Hanai. Based on our discussion, the final function that I got, the final algorithm that I have written it as a function. So let us read it out. So it is taking 4 parameters, number of disk, tower number, A, B, C are first 3 tower numbers. A, B, C are 3 tower numbers. Then if number of disks are more than 0, then perform these 3 steps. So first step is recursive call with one reduced disk, that is n minus 1, and towers are changing. See, this was from tower and this is to tower, so this is using. Now in the first step already we saw that we will move this disk from A to B. So from tower is A and B tower is 2 and C is using tower. Then move a disk from A to C. So I wrote it like this because of lack of space. Then next one, you have to move n minus 1 disks which were kept in B from B to C. So source is from is B and destination is C and A is auxiliary tower. So I will trace this one and see how this function will solve Tower of Hanai problem. And this is an example problem. Here the number of disks are 3 and tower A, tower B, tower C. I'm not calling them as A, B, C. Actually, those are variable names. So values in them are tower 1, tower 2, tower 3. So 1 and 2 and 3. So slight change here. Those are actually variable names. But in them, the values, the name of the tower, I have to take it integer. Otherwise, I should take them as characters. So instead of characters, let us take integer. So tower numbers are there. 1, 2, 3 tower numbers are there. Now, if this function is called by passing these parameters 3, 1, 2, 3. So this is n and this is A and this is B, this is C. So these 4 values are passed. So now let us trace this one. So here the first call, I will write it as a first call. Number of disks are 3 and the tower numbers are 1, 2 and 3. So these 4 values are passed. N is greater than 0, yes, n is a 3. Then what to do? Call itself by n minus 1 and the values are changed. So let us write down this call. So this is n minus 1. This is 2. First is A. A is 1. Next is C. So C is 3. And last one is B. That tower number is 2. Yes, these are changed. Now this call has to be expanded, but before expanding I will write down other 2 steps also. It will be easy for writing. Print move from A to C. So A to C. So this step is from 1 to 3. So move what is from A to C. So A is 1 and C is 3. Then third step. This is step n minus 1. So 3 minus 1, that is 2. And B first, so that is 2. Then A next, that is A is 1. And last one is C, that C is 3. So as we know the working of recursion, this call is making 2 more calls. So first call has to be finished first, then it will print this one, then it will call this one. So we know that, but we have written all of them together at once, so that's easy to write. Now let us continue. This call will be performed. So as per this call, again 3 steps, because this is 2 and 2 is greater than 0. So for that, what are the steps? So first step, ACB. So this is 1, A, C, B, right? The next, print AC, print AC. So 1 to 2, 1 to 2. See, it is not a, so last tower is not 3, it is 2. So 1 to B, it means A to B. Then this is step 1, and this is BAC, 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 3, 1, 2. This is the call. Then I'll expand this one also, though this is done afterwards. Let us expand this. So for this, first call, ACB. So this 2 will become 1, A, C, B. The next step is move A to C. So what is A? 2. C is what? 1. So 2 to 1. Then third step, n minus 1, BAC, n minus 1, BAC. So 1, 2, 3, BAC. Middle one is B. See, as per the variable names, you see the variable name A, B, C. So this is A variable name and its value is 2 now. This variable name B and its value is 1 now. So we take the values of the variables. So this B, A, C are the variable names. So this is B variable and this is A variable. This is C variable. This is written. One more level of steps I have to write, but this time the call will be for 0. 0. Now when it is 0, it has no meaning, because when it is greater than 0, it is performing. So next step will not be performed. So this call will not execute at all. So checking the towers and writing them is useless. So I will avoid writing the steps. So if I have to write, the first step is ACB, that is ACB, that is 1, 3, 2. Though it's of no use, it's going to terminate. So I will avoid this one. Then what is the next step? Printf A to C. A is 1, C is 3. 1, 3. The next step is again 0 with some values. Then for this step is 0 with some parameters, and this is move from 3 to 2. So 3 to 2. This is 1 to 3. A is 3 and C is 2. So 3 to 2. And this step is again useless. Now for this, left hand side is useless because the function will not execute. Then middle step, move A to C. So 3 to 1. Move A to C, that is 2 to 1. So 2 to 1. And this step again of no use. Then here, left hand side of no use, middle one, A to C, 1 to 3, 1 to 3, then right side 0. So actually these steps will not be performed, these will not be performed So I'll just mark them to show that these are not required. Now let us see how these calls are made and take those results. See, first this is the call, first call, then second call, then third call, then fourth call, which will not execute, so I marked it as which will not execute, so I have striken off that. Now next step is 1 to 3. So the first step is 1 comma 3. This is the first step. Then this is the fifth call. Then go back. This step is performed. So the step is 1 comma 2. So 1 comma 2 is the next step. Then this call, sixth call. Then seventh call. Then this step 3 to 2. So this is 3 to 2. Then eighth call. Then go back. And this is step 1 to 3. 1 to 3. Then next, this is the ninth call. And this is the 10th call. 11th call. Then 2 to 1. So this is 2 to 1. Then this is the 12th call. Then this 2 to 1 is printed. Oh, sorry, this was 2 to 3. I wrote it as 2 to 1. A to C, 2 to 3. So this is 2 to 3. Then 13th call, 14th call, and then this 1 to 3 step is 1 to 3. Then this is the 15th call. So total 15 calls it is making for 3 disks. But let me show you the values once again. See, first call is this one, then this call, then this call, then this call, then this value is printed. So first this value is printed, then this call, then over, then this is the next value printed, then goes back, and this is the next value printed, and this one is printed next, and then it comes on this side. So 2 to 1, and then 2 to 3, then finally 1 to 3. So the values are printed like this. So if you know the tree traversal, this is more like in order traversal. So the printing is done in order traversal. So these are the steps I got. If I follow these steps upon this problem, then the disk will be transferred from tower A to tower C with the help of tower B. So I will take these steps and show you how it works. But before showing you that, let us analyze how much time this is taking. See, there are 3 disks. Number of disks are 3. So how many calls it is making? This is making 15 calls. When n is equals to 2, how many calls it will be making? So let us look at the subset of this one. So 1, 2, 3, 4, 5, 6, 7. So it is making 7 calls. So actually for 3 itself, if you see 1, then 2, then 1, 2, 3, 4 calls, then 8 calls. So this is nothing but 1 plus 2 plus 2 square plus 2 cube. So these many calls it is making. So this is nothing but 2 power 4 minus 1. That is 16 minus 1, 15. So for n disk, how many calls it will make? I'll write them here. 1 plus 2 square plus goes on to 2 power n. So this will be 2 power n plus 1 minus 1. So this is order of 2 power n. So this is exponential time taking problem. The function is calling itself 2 times by decreased value of n minus 1. So 2 times it is calling 2 power n. So this is time consuming function. It's exponential time taking function. It takes 2 power n time. Now I will take these steps and show you how the disk can be moved. Now here are the steps that we got from the function, and here is a problem with the 3 disks and the tower numbers. You can see I have labeled them as 1, 2, 3. You can call them as ABC also. The value of A is 1, B is 2, and C is 3. So I have taken numbers, and these steps are giving numbers. Now let us follow these steps, perform these steps over this disk and get the result. First step, what does it say? Move a disk from tower 1 to tower 3. So from tower 1 to tower 3, we have to move a disk, and we know very well that we have to move only one disk. right? No need to ask how many disks. We have to move one disk only. So one disk, move it from this tower to this tower. Tower 1 to 3, 1 to 3. Second step, move a disk from tower 1 to 2. So from tower 1 to 2, which is the disk? Now the second smaller disk we have, so move that one to tower B. Over. That is from 1 to 2. The next step is 3 to 2. So third tower to second tower. Okay, move this disk from third tower to second tower. This is moved. The next step is move a disk from tower 1 to 3. From tower 1 to 3. So this largest disk you send it on tower 3. Okay. Largest disk is sent on tower 3. Now, next is move a disk from 2 to 1. So from second tower to 1. So this smaller disk, you bring it here. Then move a disk from second tower to third tower. Second tower to third tower. So this second largest disk, that is middle disk, you send it on third tower. Then move a disk from 1 to 3. So from first tower to third tower. So move a disk from first tower to third tower. That's all. I have followed these steps and all the disks are moved from here to there. See, the definition was recursive, saying that move two disks from tower A to tower B. Really, we were not moving two disks in one step. We were moving them recursively. So we have utilized one or the other towers and we have shifted the disk here and there. And finally, we got all three disks in tower C. So that was the objective. If you're not following the steps, if you're randomly trying to do, we may be wasting our time by performing unnecessary steps or repeating steps. That is the problem. Now, recursion gives us perfect minimum number of steps, exact number of steps. If you follow that, you can move the disk from one tower to another tower. Now, that's all about tower of Hanai problem. Now, for you to remember it, you have to work on this one. So practice this one once and then you can easily remember this one. And this idea will help you solve other problems. This Tower of Hanai idea will help you think recursively. In this video, we will have a demonstration for Tower of Hanai problem. So I will write on the function, recursive function, which we have seen. Void TOH, Tower of Hanai. First is number of disk and next is tower number. So first tower number will be A, the next tower number is B and next is C. Now first is if number of disks are greater than 0, then only perform these steps. So the first step is Tower of Hanai, call itself for n-1 disk and see this three tower names. A to C we have to move using B. So here first move from A to B but using C, so C should come in between. So this is the first recursive call. Then printf, so here I write statement move. See, instead of writing move, I'll do just one thing. I'll just write a order pair, %d, comma, %d. These are the order pairs that we have generated at last. So slash n, this one. Now here the tower is A and destination tower is C. This will print order pairs. Then that is from tower to tower, that is source tower to destination tower. Then Tower of Hanai is recursively called for n-1 disk and here we have to move the disk from tower B to tower C and utilize tower A. So tower A comes in between. So that's all. This is a very simple function. Now inside the main function I will call Tower of Hanai by passing 3 disks and the tower numbers I will give them as 1, 2, 3. So first value is number of disks, then remaining 3 values are tower numbers. Let us run the program and see what the output we get. See, 7 steps we got for moving 3 disks from tower A to tower C. these are the steps which we have already saw them in the previous video. Also, I have used these steps for moving the disk from tower A to tower C. So the program is just giving the steps to be taken for moving the disk. It is not moving the disk, it is giving us a step. So following those steps, we should move the disk to solve this problem. If I change the number of disks to 2, let us see what happens. See, move a disk from tower 1 to tower 2, then 1 to 3, then 2 to 3. That's all. These are the steps we have seen for 2 disks. If I give the number of disks as 1, then what happens? So directly from 1 to 3. There is a single step for 1 disk. Move a disk from tower 1 to tower 3. So if I give 4, then let us see how many steps I'll get. Yes, these many steps are there. I guess these are 15 steps total. So you can count them, you can check it. That's all about Tower of Hanoi problem. Yeah, in this video, I will show you the solutions for the questions given in quiz. So I have some questions in the quiz upon recursion. So let us solve them, right? I will trace and solve them. So hope you have done it already, but just to confirm your results, or if you have missed anything, so you can understand where you have gone wrong. So let us do it. I have first question here. This is the first question. This is a recursive function, and this is called for f of 1. So we want the result, what the function will return. What is the result of a function if it is called for 1? So this is a function. Okay. Recursive function, how to trace, already have shown you. So the tracing tree will be prepared, right? So let us start preparing tracing tree. F of 1. So first is f of 1. Then inside the function, if you see, there is a static variable. So already in one of the video I have discussed about the static variables in the recursive function. They will maintain on a single copy. So this I, only one copy will be maintained. So don't put it in the tracing tree, separately keep I here. So this is a, treat it just like a global variable. So its value is 1. That's it. Now start. If n is greater than or equal to 5, then return n. N is what? Now 1. N is 1. And it is not greater than or equal to 5. The next step, n assign n plus I. So I will change it. N is what? 1. So 1 plus I. I is how much? 1. So n becomes how much? 2. This is 2. N is 2 right now. Then I plus plus. So where is I? It is static. So here it should become 2. I am writing it here. So I became 2. Then return. Return what? F of n. So again the function is called for the value of n. So this is a recursive call. So I plus plus is there. So I have not shown it here. If you want, you can show it, right? So I am showing all the steps now. This one and this one and this one. Now next is call for 2. N is 2. Function is called again for 2. Then this is the declaration. This is over. Because it is static, it is done only once, right? So it is not done again. Again, don't think that I becomes 1. If you are doing it, then you get wrong answer. That is static. It is done only once. Now, right now, the value of I is 2. We are not in the first call. We are in the second call. Yes, that is static. It remains as it is in the second call also. Yes. Then, n, is it greater than or equal to 5? Is it greater than or equal to 5? No. Then these 3 steps. So first step is what? N assign n plus I. N plus I. What is n? 2. What is I? 2. So how much is n now? N is 4. The next step is I plus plus. So I plus plus, I'll make this as 3. Then next, call again itself for fun of n. What is n right now? 4. 4. Now let us do this step quickly. This is over already, right? I is right now 3. N, is it greater than or equal to 5? No, it is not greater than or equal to 5. Then n assign n plus I. N is how much right now? 4. So 4 plus I is how much? 3. So this is how much? 7. Then I plus plus. So I plus plus makes this as 4. Then call function f of n. What is n? 7. Now it comes here with 7. 7 greater than or equal to 5? Yes, it is greater. So do what? Return n. What is n? 7. Return n. So 7 is returned here. Then in this statement, if you see, this was the statement, right? So what is written here? Return. So whatever the result is obtained, that is returned. So 7 is returned from here also. So it is 7 here. Then again, this is the same statement. Same statement. From here only we have called. So return from here also. So this is return. So this is 7. So finally, the answer for this one is 7. So the result of this function is 7. So if you have not maintained a single copy of I, then you might have got wrong results, right? So this is the result, that is value 7. So answer for this is 7. Let us look at second question. So here is a program, that is second question of quiz. It is a little lengthy. Let us trace this program. See, here is a main function and also a function foo. So main function is calling foo. So let us look at the data members or the variables of main function. So what are the variables of main function? A, which is having value 2048. Then sum, which is having value 0. And these belongs to main. I'll write them here. This belongs to main. Now main function call foo by passing a and sum. A and sum. So a goes into n and sum goes into that sum. First and the foremost thing, is it called by value, called by reference, or called by address? What it is? This is called by value. Here stars are not written, so this is not called by address. Ampersands are not there, so this is not called by reference. This is called by value. So let us trace this function foo now. So here foo is called. So first value a is 2048 and sum is 0. So two variables, n will have 2048 and sum will be 0. Then if n is equal to 0, return, it's going to stop. Return means stop, and this is void type. It's not going to return any value. Return means just stop. Then how many steps are there? 1, 2, 3, 4, 5 steps are there. So let us perform these steps. First step, k assign n mod 10. So what will be the value of k? Mod 10, how much it is? If you divide this number by 10, then remainder will be 8. So mod is 8. The next step, j assign n divided by 10. So j assign n divided by 10. So n is 2048. So when you divide it by 10, 8 will be gone. It will be 204. So j will be 204. Sum assign sum plus k. So what is the value of sum? 0. Sum plus k. So 0 plus k. So sum will be 0 plus k is how much? 8. So sum will be 8. The next step, call itself for j and sum. Call itself for j, that is 204, and sum is how much? 8. Then one more step, print k. So this step will not be performed now because it has called itself. So this will be performed at returning time. So we will do it at returning time. So I'll just leave a line here. Here we have to print k. So whatever the value of k, that it will be printed. Not now, at returning time. So let us continue with this call now. This call. In this call also same steps, right? Same steps. So k assign mod 10, j assign divided by 10, and in sum k is added. So k assign mod 10, so 4. J assign divided by 10, so 20. Sum assign sum plus k. 8 is a sum plus 4, so this is 12. Then call itself for next values, that is j and sum. So 20 and 12. And also print. That printing will be done afterwards. So all the steps I have done. 1, 2, 3, 4, 5. 1, 2, 3, 4. Fifth one will be done at returning time. Now continue. This one, this call. It will make this call. Again these steps. So k assign mod. So 20 mod 10 is how much? 0. And 20 divided by 10 is how much? 2. So it gets 2 times divided. Then sum assign sum plus k. Sum is 12. 12 plus 0 is 12 only. Then call itself for j and sum. So 2 comma 12. And also it has to print. I'll just remove this. It has to print. Print will not be done now, it will be done afterwards. Now one more call. So this one, again those steps. K assign n mod 10. 2 mod 10 is how much? 2 only. J assign n divided by 10. 2 divided by 10. So J value will be how much? 0. Then sum assign sum plus K. So sum is right now 12. So in that 2 is added. So this becomes 14. Then one more call with the foo. So I have to remove this also, right, to just make a space. You know very well about this. Then foo, one more call. What is that? J and sum 0 and 14. And also it has to print. This will be done afterwards. Now this call, when it comes here, n is equals to 0, return. This has stop. It will not call further. This will stop. This call will not go further. So it will come back to this call. So what it has to do remaining? Print K. So what is K? 2. So 2 is printed. Then this finishes. This is the end, right? This is the end. Then go back to the previous call and perform this step. So what is that step? Print K. How much it is? 0. So this is 0. Then this finishes. Go back to the previous call in this one. So this is remaining. Print K. What is K? 4. So print 4. Then go back to the previous call. This is remaining. So print K. What is K? 8. 8. 2048. And this function ends. Function ends. So this tracing is over. It returns back to the main function. This is the main function. From here it was called foo. From here it was called. Now, next step. Print sum. Which sum? Main function sum. How much it is? 0. This is not change. No, it became 14. This was belonging to foo function. It doesn't belong to main function. Main function sum is 0 only. It is called by value. It is not modified. So print sum is 0. Yes, this is the answer. 2048 and 0 is printed. If you got this answer, then it is perfect. If you got the answer that is 2048 and 14, means you have mistaken. You thought that this sum is modified. We are adding this one. No, that is belonging to foo function. It's nowhere related to this. So this is not modified. So that's all. This is the tracing. This is little bit lengthy, right? Because so many operations are there in the function, and the result is 2048 and 0. Now let us look at third question. Let us look at the third example, third question from quiz 1. This is the program given there. This is the example. So let us study this one. See, this is the main function. I have not given in the question, but for explanation I have written it here. In description, it's everything is there. So it says that if P is having value 5 and it is passed one value by a reference and other value by value. So yes, P is there. This belongs to main function. So let us draw it. Okay. P is having value 5. Then function f is called by passing P 2 times. But the first time is by reference. You remember this reference, right? C++ reference. Then this is by value. One is by reference, other one is by value. So those two are passed. So it is nothing but P only passed. Now these are the statements. So let us trace this one. So I will write on that function f. Okay. First one is x and the second one is called by value. See, in the tracing of function, if it is by value, I have directly written the value. So what is the value of a P5? So that C will have the value 5. So let us write 5 here. Okay, I don't have to write C. But that X is a reference. Don't write 5 there. If it is reference, don't write it. So that X is nothing but referring to this P only. This is P only. That P actually belongs to main function. This is the important thing in this function. If you have understood this, then you can trace it perfectly. Now let us trace it. First step, C assign C minus 1. So what C becomes? C was a 5, right? Minus 1 means C becomes 4. If a C is equals to 0, no, otherwise it should return 1. It's not 0. Then X assign X plus 1. So X assign X plus 1 means X will increment. So what is X? This one. So this should increment and it should become 6. I made it 6. Then call function fun by f of x comma c. Call again itself by passing f of x comma c. C is what? 4. Then why I'm writing x? Because that x is nothing but reference to this p. It's a reference to this p. Every time when I say x, I will come here. Okay. Then into x is there, so I will keep it as it is. I will not take the value and multiply, because it will not be multiplied right now. When the multiplication will be done, at returning time it will be done. So because this is done after getting the value, then you can multiply. Otherwise, if you want to multiply now, right now x is how much? 6. 6 into what? What you will multiply? So first of all, this value should be there, then it can be multiplied. So don't write 6, let it be x only. That time only we will see. When it has to multiply, that time it will go to p and get the value. Okay, so leave it as it is. Now this call we have to continue further. So this was the first call I have explained in detail. Now remaining calls, just I'll repeat them. X comma 4, c assign c minus 1. So c becomes how much? 3. Then c, is it 0? No. So x assign x plus 1. So x assign x plus 1 will make it as 7, because this x is nothing but this one. Then call itself again by passing x comma c value is 3 and into x. One more call. Then in this call again c assign c minus 1. So c becomes how much? It is 3, so it becomes 2. Then next is x assign x plus 1. So this becomes 8. Then again it will call itself x comma c is 2 into x. We will see it afterwards. Then again call. So x comma 2 assign 2 minus 1. So c becomes how much? 1. C, is it equal to 0? No, not 0. Then enter inside x assign x plus 1. So x becomes how much? X assign x plus 1. So this x is nothing but p only, right? You remember? 9. Then again call itself by passing f, and that is x comma c is how much? 1. Then into x. I'm keeping it x only every time, right? I'm not taking the value. Then this one, x comma 1, x comma 1, c assign c minus 1. So c becomes how much? 0. Is the c equal to 0? Yes, c became 0. Return 1. So this function returns 1. So now from here it will return back. So this returns means the same function value becomes 1. 1 into x. What is x now? 9. 9. This is 9. This 9 is returned. So this is the result. This is 9 into x. Now you go to x. What is x? 9 only. So this is into 9. So this is 9 square. So this is returned to this one. So this is 9 square into x. What is 9? X, right? 9 only. So this is 9 cube. And this is returned. So this is 9 cube into x. What is x? 9 only. So this is 9 power 4. And this is returned. So this is 9 power 4. Yes, this is the answer. So the answer returned by, so 9 power 4 is 6561. So yes, this is the answer for this question. Now, if you got wrong answer, means you have not done it properly. You have not referred to this one every time. And one more reason of getting wrong answer is you are writing the values here. First time it was 6, then you wrote 7, then 8, then 9. So 6, 7, 8, 9. So you are multiplying these values. So it's wrong. And one more mistake that you may be doing it, you are increasing up to 10. Here also you are doing it up to 10. So commonly this type of mistakes are possible if you are not solving it properly. So this is the answer for this quiz question. Next, we will go to the next question. Now next quiz question is this one. A function is given and we have to find out what is the result of this function if it is called for 5, value 5, by sending value 5. So we have to trace this one. Let us do it. First time I am sending 5. So fun of 5. Fun of 5. Then these are local variables. Yes, these are not static. So in every call x will become 1. Remember this. K is also newly created in every call. Okay, we will use them. N is equal to 1, return x. No, it is not 1. Then For k assign 1 to less than n. 1 to less than n means 1, 2, 3, 4. So for k assign 1, 2, 3, 4, these statements are repeated. So 1, 2, 3, 4, so many times they are repeated. So let us do it. This is x assign x plus what? First one. First one is what? Fun of. K value is what? K value is 1. So this is fun of 1 comma n minus 1. So what is n? 5. Fun of 1 into fun of 4. Then plus, because this is going to be added into x every time. So again one more time. So that time k is how much? 2. Right now k is 2. So this is fun of 2 into fun of 5 minus 2. That is 3. Then plus. This is in for loop. Repeat. One more time. One more time. So this is, I'll continue here. There is no space. So fun of k will be what? 3. So this is 3 into fun of 5 minus 3 is 2. Then plus. One more time. Now this time k will be 4. So fun of 4 into fun of n minus 1, that is n minus k, that is 5 minus 4, it is 1. So many calls for just fun of 5. So many calls are there. This is complex. You cannot solve it easily by using pen and paper. So in this you should finish this one, then this one. So don't know how much expansion this will take, and this one and this one. All these you should know, then multiply and get the result. So this is not easy. It's not easy. Then how to solve it? So for solving this one, we'll take another approach. Let us see this one. So here I will take the values of fun of n, and for the values of n, so I'll make it as a table. Let us do it. Then I'll tell you why I'm taking table. So first, see what is the minimum value? N is equals to 1. If n is equals to 1, if I call this function by passing 1, not 5, if I call it by passing 1, then what happens? Let us get that value. Okay, so first we will find smaller value. Then slowly we'll increase and get the value for 5. Yes, that is the idea. So when n is 1, what is the result? Return x. What is x? 1. So it is 1. Answer is 1. So now we know fun of 1 is 1. Fun of 1 is 1, right? The next, fun of 2. We need this also, right? So I'm not making a tree. I'm making a table. So let us find fun of 2. So fun of 2 means what? So 2 means it is not 1. It will enter here. So how many times this loop will repeat? K as 1, right? K as 1 up to less than 2. So it will repeat only for one time. So let us do it. So for fun of 2, it will be x plus, right? Fun of k is what? 1. K is 1 into fun of 2 minus 1. K is 1, right? Only one time it will repeat. Just observe that, right? There is nothing to explain. You have to read and understand it. So this for loop will repeat for only one time. That statement I wrote here. So what are the values? It's only this much, that's all, only one time. So how much it is? This is x is how much? 1. Fun of 1. Here we already know fun of 1 is 1. Okay, take it as 1 into fun of 2 minus 1. 2 minus 1 is what? 1. This is 1. Oh, this is again fun of 1. Already we know it. How much it is? 1. So this is 1 plus 1 into 1. So 1 plus 1 into 1 is how much? 1 plus 1, that is 2. Yes, fun of 2 is 2. So we got the result. So we have fun of 1 also, fun of 2 also. Let us find fun of 3. Let us find fun of 3. 3. So fun of 3. When it is a 3, x plus, it is not 1. So it will enter inside. So this k takes values from 1 to 3. So how many times it will repeat? 1 and k less than 3 means 1 and 2. 2 times it will repeat. So k will take 2 values. One time 1, second time 2. Let us put it here. So x plus fun of k is 1. and fun of n minus k. So what is n? 3, right? 3. So 3 minus 1. Plus, one more time it will repeat. So plus, it will be accumulated in this one only, added in this one only. So this time, fun of k is how much? 2. Take it as 2. So this is 3 minus 2. So fun of 2 into fun of 3 minus 2. Okay, I'll remove this. So now let us solve it. This is 1. Okay, 1 plus fun of 1. We already know it is 1 into what is this? Fun of 3 minus 1. 3 minus 1 is 2. Fun of 2. What is the value of fun of 2? We know it. Say this is the benefit. We already know smaller value. So this is 1 into 2 plus fun of 2. It is 2. Just now we wrote it. 2 into fun of 3 minus 2. 3 minus 2 is how much? 1. Fun of 1 is what? 1. Then total how much this is? 1 plus 1 into 2, 2 plus 2 into 1 is 2. So this is 5. So we got the answer as 5. So this is 5. Now next is fun of 4 and then fun of 5. That's how you can get it. Now for fun of 4, I will not write all these things. Directly I will write on the answer. Okay. Then also for fun of 5. So I'll remove this and I will use this place. Fun of 4. 4 means k takes values from 1 to less than 4. So k is going to take the values 1, 2 and 3. So let us start. X is 1. First time fun of 1 into 4 minus 1. So f of 1 into 4 minus 1. So 4 minus 1 is what? 3. Plus f of k is a 2 now. So into 4 minus 2 is a 2. Plus f of 3. K is 3 right now. So 3 means f of 4 minus 3 is 1. So how much this is? So let us add this. This is 1. Fun of 1 is how much? 1 into fun of 3 is how much? What? 5. Plus fun of 2 is a 2. So this is 2 into 2. Plus fun of 3 is a 5 into fun of 1 is 1. So how much this is? 5 plus 5, 10. 10 plus 4, 14 plus 1, 15. So this is 15. Then fun of 5. Fun of 5 is how much? 1 plus. Now k will take the values 1, 2, 3 and 4. So f of 1 is 1. F of 4 is, see it is like this, 1 is multiplied with 4. So f of 4 is 15 plus 2 with 3. So 2 with 3 means 2 into 5. 2 into 5. Then plus, then 3 into 2. So 5 into 2. 5 into 2. If you have observed this, then you can directly write this. Then 4 into 1. So 15 into 1. 15 into 1. How much this is? 1 plus 15 plus 5 to 10 and 5 to 10 and this is 15. 15, 15, 30, 40, 50, 51. So the answer is 51. So this is 51. That's it. This is the answer. So the main idea here is that we cannot find the result by expanding it. We cannot do that. Then we have to start finding the smaller values, then we can get this one. So that's all in this question. Now one more question is there. So let us look at the next question in quiz 1. Now let us look at next question in quiz 1. See, this is the program given, this is a function and it is called for value 3. If you read this, the variables are n and d. Only 2 variables are there. But d is static. So you remember, when you have any static variable, you should take it separately. So let us put it as 1. Now what is there inside? Just printfs are there. So okay, it's easy. Let us do it. So let us make a first call. C of 3. Instead of count, I am saying just C. Okay. So C of 3, count of 3. Static, D is 1. Yes, this is over. This is initial, right? We don't have to repeat it every time. Print n. So what is n? 3. So print 3. Okay, here I will write on the output what we get. So first time 3 is printed. Then print D. What is a D? It is printed now, right? So D value, what is that? 1. So 1 is printed. So 1 is printed. Then D plus plus. D plus plus. D becomes 2. If n is greater than 1, then count n minus 1. So yes, it is greater than 1, it is 3. So count is called again for n minus 1, so it is for 2. The next print, but first of all call is there. Finish that call and then print. Okay, printing will be done, but not now, afterwards. Then call for 2. Continue from here. Again it calls itself. So again printing is there. So first print n. N is how much? 2. So 2. Next print D. D is how much? 2. So 2. Then D plus plus. D plus plus. D becomes 3. N is greater than 1? Yes. Call itself for n minus 1. So C is called for n minus 1. 2 minus 1, 1. Then after that printing is there, but not now. It will be done afterwards. See, here also we left it. We have to do it afterwards. This time C is 1. Come again. Right? Print n. N is what? 1. Print 1. Then print D. D is how much? 3. So print 3. Then D plus plus. So this is okay. 1 is printed and 3 is printed. Then D plus plus. So D plus plus. D becomes how much? 4. Then n is greater than 1? No, it's not greater than 1. So it doesn't call. So calling is not done. But after that printing is there. So printing is done. So what is a D? 4. So now this is the end point, right? It's going to print now. So it is 4. 4 is printed. There is no call further. Go back. So it goes back to the previous call. So for this call, this is completed. Next is there remaining. Print. This is print. Print what? D. What is D? 4. So 4 is printed now. Then this call finishes. It goes back in this line, right? This one, this line. For this call. It is in this call now. This is over. Next is remaining. What is that? Print. Print what? D. D is how much? 4. So 4 is printed. So this is 4. So the answer is 3 1 2 2 1 3 4 4 4 is the answer. So that's all. This is the tracing and explanation of all quiz questions, right? So you can write this program and test them also. You get the same result. So that's all with quiz 1 problems.